What if I told you that somewhere out there, billions of light years away, there's a black hole so massive it could devour entire galaxies without breaking a cosmic sweat? These distant black holes lurking at the edge of the observable universe are not just mysterious, they're time capsules, holding secrets about the earliest moments of existence itself. And today, we're diving into 50 mind-blowing facts about these cosmic giants that will leave you questioning everything you thought you knew about space. From black holes that spin faster than the speed of light to ones so ancient they existed when the universe was just a baby, we're about to uncover the wildest, most fascinating truths about these distant enigmas. Whether you're a space enthusiast or just someone who loves a good cosmic mystery, this journey will take you to the farthest reaches of the universe and maybe even beyond. So buckle up and get ready to explore the universe's most distant black holes. By the end of this video, you'll not only understand why these cosmic monsters are so important, but you'll also see the universe in a whole new light. Let's dive in. Now, let's start with the basics. What exactly is a black hole? Imagine a place in space where gravity is so strong that nothing, not even light, can escape its pull. That's a black hole. At its core lies something called a singularity, a point where matter is crushed to infinite density. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape. Think of it as the point of no return. Once something crosses that line, it's gone forever. But what makes distant black holes so fascinating? Well, these cosmic behemoths are not just powerful, they're also incredibly old. When we observe a black hole billions of light years away, we're essentially looking back in time, seeing it as it was when the universe was much younger. This gives us a rare glimpse into the early stages of cosmic history, helping us piece together how the universe evolved. Distant black holes also challenge our understanding of physics. Their immense gravitational pull warps space and time, creating effects that seem almost magical. And because they're so far away, studying them pushes the limits of our technology and imagination. So, while all black holes are mysterious, the ones at the edge of the observable universe hold secrets that could rewrite the rules of science as we know it. With that in mind, let's move on to how these distant black holes were first discovered, a story that's as fascinating as the black holes themselves. Now, let's take a step into the past and explore how astronomers first uncovered the existence of distant black holes. The journey to discovering these cosmic giants wasn't easy. It required groundbreaking technology and a lot of patience. The first distant black holes were detected using powerful telescopes like the Hubble Space Telescope, which allowed scientists to peer deep into the universe. These telescopes captured light that had traveled billions of years to reach us, revealing the presence of black holes in galaxies far, far away. But telescopes weren't the only tools in the astronomer's toolkit. Gravitational wave detectors like LIGO and Virgo played a crucial role in this discovery. These instruments detect ripples in space-time caused by massive cosmic events such as black hole mergers. When two black holes collide, they send out gravitational waves that travel across the universe, giving us a way to hear these distant phenomena. This combination of light and gravitational waves opened up a whole new way to study black holes, allowing us to see and hear the universe in ways we never could before. The discovery of distant black holes wasn't just a scientific breakthrough, it was a testament to human ingenuity. By combining observations from telescopes and gravitational wave detectors, astronomers pieced together a clearer picture of these enigmatic objects. And with each new discovery, we're not just learning about black holes, we're uncovering the history of the universe itself. Next, we'll dive into the oldest known black hole ever discovered, a relic from the early days of the cosmos that holds clues to how the universe began. Now, let's travel even further back in time, to the very edges of the universe's infancy and meet the oldest known black hole ever discovered. This ancient cosmic giant, known as UHC-1, is estimated to be around 13.8 billion years old, forming just a few hundred million years after the Big Bang. To put that into perspective, this black hole existed when the universe was still in its toddler phase, a time when galaxies were just beginning to take shape. What makes UHC-1 so remarkable isn't just its age, it's the clues it holds about the early universe. This black hole is a supermassive one, weighing in at millions of times the mass of our Sun. But here's the puzzle: how did it grow so massive so quickly? According to our current understanding, black holes need time to grow by consuming matter and merging with others. Yet, UHC-1 defies this logic, suggesting that some black holes might have formed differently in the early universe, perhaps from the direct collapse of massive gas clouds or other exotic processes we're still trying to unravel. Studying UHC-1 is like opening a time capsule from the dawn of the cosmos. It gives us a glimpse into a time when the universe was a chaotic, rapidly evolving place. By analyzing its light, which has traveled for billions of years to reach us, astronomers can piece together the conditions of the early universe and test theories about how the first black holes and galaxies formed. This ancient black hole isn't just a scientific curiosity, it's a key to understanding the origins of everything we see today. And as we continue to explore the universe's most distant corners, who knows what other secrets from the past we might uncover? Next, we'll explore how quasars, the brilliant beacons powered by supermassive black holes, help us detect these distant cosmic giants and reveal even more about the universe's history. Now, let's turn our attention to one of the most dazzling phenomena in the cosmos: quasars. These brilliant beacons of light are not just cosmic showstoppers, they're also some of the most powerful tools we have for uncovering the secrets of distant black holes. Quasars are essentially the blazing cores of distant galaxies, powered by supermassive black holes at their centers. As these black holes devour surrounding matter, they release staggering amounts of energy, making quasars some of the brightest objects in the universe. But how do quasars help us detect distant black holes? The answer lies in their incredible brightness. Even though these black holes themselves are invisible, since not even light can escape their grasp, the intense radiation from the quasars they power can be seen across billions of light years. This makes quasars like cosmic lighthouses, guiding astronomers to the supermassive black holes lurking in the distant universe. Quasars also act as time machines, offering us a glimpse into the universe's past. Because light takes time to travel, the light we see from a quasar today may have left it billions of years ago. By studying the light from these ancient quasars, astronomers can piece together the conditions of the early universe, including how black holes and galaxies formed and evolved over time. What's even more fascinating is that quasars reveal the dynamic relationship between black holes and their host galaxies. The energy emitted by quasars can influence the formation of stars and even regulate the growth of galaxies themselves. This feedback process, where black holes and galaxies shape each other, is a key piece of the puzzle in understanding how the universe has evolved into the complex web of structures we see today. So, while quasars may seem like distant, otherworldly phenomena, they're actually vital tools for unlocking the mysteries of the cosmos. They not only help us detect the universe's most distant black holes, but also provide a window into the universe's history, showing us how everything from stars to galaxies came to be. Next, we'll journey even further into the cosmos to uncover the farthest black hole ever observed, a record-breaking discovery that pushes the boundaries of what we know about the universe's most distant corners. Now, let's venture even deeper into the cosmos to uncover the farthest black hole ever observed, a discovery that stretches our understanding of the universe's most distant frontiers. This record-breaking black hole, known as UHC-1, sits an astonishing 13.4 billion light-years away from Earth. To put that into perspective, the light we see from this black hole today began its journey when the universe was just a fraction of its current age, a mere 600 million years old. Detecting such an incredibly distant black hole is no small feat. Astronomers relied on a combination of cutting-edge tools, including the Chandra X-ray Observatory and the James Webb Space Telescope. These instruments work together to peer through the vast expanse of space, capturing the faint signals emitted by the black hole's surrounding environment. What makes UHC-1 particularly fascinating is that it's not just a black hole. It's a supermassive one, weighing in at around 10 million times the mass of our Sun. But how do we even know it's there? Black holes themselves are invisible, but their presence is revealed through the effects they have on their surroundings. In the case of UHC-1, the black hole's immense gravity heats up the gas and dust around it, causing it to emit X-rays. These X-rays, though faint after traveling billions of light years, are what Chandra detected. Meanwhile, the James Webb Space Telescope provided crucial data about the black hole's host galaxy, helping astronomers confirm its distance and age. This discovery is more than just a cosmic milestone, it's a window into the early universe. UHC-1 challenges our understanding of how supermassive black holes form and grow. How did a black hole of this size exist so soon after the Big Bang? Current theories suggest that these cosmic giants may have formed from the direct collapse of massive gas clouds, bypassing the usual star formation process. This discovery pushes the boundaries of our knowledge and raises new questions about the origins of black holes and the universe itself. As we continue to explore the farthest reaches of space, discoveries like UHC-1 remind us just how much we still have to learn. Next, we'll dive into the fascinating process of how black holes form, shedding light on the conditions that give rise to these cosmic giants. Now, shifting our gaze from the farthest reaches of the cosmos, let's explore the very origins of these enigmatic giants, how black holes come into existence. The formation of black holes is a cosmic dance of gravity, mass, and extreme conditions, and understanding it sheds light on why distant black holes like UHC-1 are so extraordinary. Black holes form under some of the most extreme conditions in the universe. The most common path begins with the death of a massive star. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against the crushing force of its own gravity. The star's core collapses in on itself, triggering a cataclysmic explosion known as a supernova. What remains after this violent event is a dense, compact object, a black hole. But not all black holes form this way. Distant black holes, like the ones we've been discussing, often grow to supermassive sizes, and their formation is a bit more mysterious. In the early universe, massive clouds of gas and dust may have collapsed directly into black holes, bypassing the star formation stage entirely. This process, known as direct collapse, could explain how supermassive black holes like UHC-1 grew so large so quickly. Another key factor in black hole formation is the environment. In the dense, chaotic conditions of the early universe, galaxies were packed closer together, and collisions between them were more frequent. These collisions could have funneled vast amounts of gas and dust into the centers of galaxies, providing the raw material needed for black holes to grow. Over time, these black holes could have merged with others, growing even larger and more powerful. What's truly fascinating is that the formation of black holes isn't just a one-time event, it's an ongoing process. Even today, black holes continue to grow by consuming nearby matter, merging with other black holes and pulling in gas and dust from their surroundings. This constant evolution makes black holes some of the most dynamic and influential objects in the universe. As we piece together the story of how black holes form, we gain a deeper appreciation for the forces that shape the cosmos. Next, we'll delve into the role of dark matter in the lives of these cosmic giants, uncovering how this mysterious substance influences their growth and behavior. Now, let's turn our attention to one of the most mysterious components of the universe, dark matter, and its intriguing relationship with distant black holes. Dark matter, which makes up about 27% of the universe, doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its gravitational influence is undeniable, shaping the very fabric of the cosmos and playing a crucial role in the formation and growth of black holes, especially those in the distant reaches of space. Dark matter acts as a cosmic scaffold, providing the gravitational framework that allows galaxies and their central black holes to form. In the early universe, dark matter clumped together, creating dense regions that attracted gas and dust. These regions eventually collapsed under their own gravity, forming the first galaxies and, at their centers, the seeds of supermassive black holes. Without dark matter's gravitational pull, the universe as we know it and the black holes within it might never have come into existence. But dark matter's influence doesn't stop there. It also plays a key role in feeding and growing black holes over time. As galaxies evolve, dark matter halos, vast, invisible clouds surrounding galaxies, continue to pull in gas and other matter. This material funnels toward the galactic center, where it can be consumed by the supermassive black hole, fueling its growth. In this way, dark matter acts as a cosmic delivery system, ensuring that black holes have a steady supply of material to devour. Interestingly, dark matter might also help explain why some distant black holes grew so massive so quickly. In the early universe, dark matter halos were denser and more concentrated, creating environments where black holes could rapidly accumulate mass. Some theories even suggest that dark matter itself could collapse directly into black holes under certain conditions, providing another pathway for their formation. While this idea is still speculative, it highlights the deep connection between dark matter and the evolution of black holes. As we continue to study dark matter and its interactions with black holes, we uncover more about the invisible forces that shape the universe. Next, we'll explore how the speed of light affects our observations of distant black holes and why they appear as they did billions of years ago, offering us a glimpse into the past. Now, let's shift our focus to the fascinating interplay between the speed of light and our observations of distant black holes. Light, as we know, travels at an astonishing speed, about 300,000 kilometers per second. But even at this incredible pace, the vast distances across the universe mean that the light we see from distant black holes has been traveling for billions of years. This means that when we observe these cosmic giants, we're essentially looking back in time, catching a glimpse of the universe as it was in its younger days. The speed of light plays a crucial role in how we perceive distant black holes. Because light takes time to travel, the farther away a black hole is, the older the image we see. For example, when we observe a black hole located 10 billion light-years away, we're seeing it as it existed 10 billion years ago. This time delay allows astronomers to study the early stages of the universe, providing valuable insights into how black holes formed and evolved over cosmic history. But there's more to it than just a time delay. The speed of light also affects how we interpret the behavior of distant black holes. For instance, the intense gravitational pull of a black hole can bend light, a phenomenon known as gravitational lensing. This bending of light can magnify or distort the appearance of distant black holes, making them appear larger or brighter than they actually are. By studying these distortions, scientists can learn more about the mass and structure of black holes, even those located billions of light-years away. Another intriguing aspect is how the speed of light influences the energy we detect from distant black holes. As light travels through the expanding universe, its wavelength stretches, a process called redshift. This means that the light emitted by a distant black hole billions of years ago reaches us as lower energy radiation, often in the form of infrared or radio waves. By analyzing this redshifted light, astronomers can determine not only the distance to the black hole, but also its velocity and the rate at which the universe is expanding. The speed of light, while constant, creates a unique window into the past, allowing us to observe distant black holes as they were in the early universe. This time-traveling aspect of astronomy is one of the most powerful tools we have for understanding the origins and evolution of these enigmatic objects. Next, we'll dive into the immense sizes of distant black holes and how they compare to those closer to home, revealing just how colossal these cosmic phenomena can be. Now, let's take a moment to marvel at the sheer size of distant black holes and how they stack up against their counterparts closer to home. When we talk about black holes, we're dealing with some of the most massive objects in the universe, but distant black holes take this to an entirely new level. These cosmic giants are not just big, they're mind-bogglingly enormous, often dwarfing even the largest black holes in our own galactic neighborhood. To put this into perspective, consider the supermassive black hole at the center of our Milky Way, known as Sagittarius, a star. This black hole has a mass equivalent to about 4 million times that of our Sun, which is already staggering. But distant black holes, especially those found in the early universe, can have masses billions of times greater than our Sun. That's right, billions. These supermassive black holes are so massive that they challenge our understanding of how such colossal objects could have formed so quickly after the Big Bang. One of the largest distant black holes ever discovered is located in a quasar known as TUN 618. This behemoth has a mass estimated at around 66 billion times that of our Sun. To give you a sense of scale, if you were to place TUN 618 in the center of our solar system, its event horizon, the point of no return would extend far beyond the orbit of Pluto, engulfing everything in its path. It's a scale so vast that it's almost impossible to fully grasp. But what makes distant black holes so much larger than those closer to us? Part of the answer lies in their age. Many of these distant black holes formed during the early universe, a time when conditions were ripe for rapid growth. They had access to vast amounts of gas and dust, which fueled their expansion over billions of years. Additionally, mergers between black holes and galaxies in the early universe likely contributed to their immense size, creating these cosmic titans that we observe today. Interestingly, the size of a black hole isn't just about its mass, it's also about its influence. Distant black holes, with their enormous gravitational pull, play a crucial role in shaping the galaxies around them. They can trigger star formation, regulate the flow of gas, and even influence the structure of the cosmic web on a grand scale. Their size isn't just a curiosity, it's a key factor in understanding how the universe evolved over billions of years. As we continue to explore these distant giants, one thing becomes clear: the universe is full of wonders that push the boundaries of our imagination. Next, we'll delve into how these distant black holes impact the galaxies they inhabit, revealing the intricate dance between these cosmic behemoths and the stars around them. Now, let's shift our focus to the profound impact these distant black holes have on the galaxies they call home. It's not just their size that makes them fascinating, it's the way they shape the very fabric of the universe around them. Distant black holes, with their immense gravitational pull, act as cosmic architects, influencing the formation and evolution of galaxies in ways that are both dramatic and subtle. At the heart of many galaxies, including those in the distant universe, lies a supermassive black hole. These black holes don't just sit idly by, they actively interact with their surroundings. One of their most significant roles is in regulating star formation. You might think that black holes, with their destructive reputation, would only hinder the birth of stars, but the reality is far more nuanced. In some cases, the intense gravitational forces and energy emitted by these black holes can compress gas clouds, triggering the formation of new stars. It's a delicate balance. Too much activity, and the black hole can heat up the surrounding gas, preventing it from cooling and collapsing into stars. But just the right amount of energy can create the perfect conditions for stellar nurseries to flourish. Distant black holes also play a crucial role in shaping the structure of galaxies. Their gravitational influence can cause gas and dust to spiral inward, feeding the black hole and creating what's known as an accretion disk. This disk emits enormous amounts of energy, often in the form of powerful jets that shoot out from the black hole's poles. These jets can travel vast distances, carving out cavities in the surrounding gas and influencing the distribution of matter within the galaxy. Over time, this process can alter the galaxy's shape, density, and even its ability to form new stars. But the influence of distant black holes doesn't stop at the galactic level. They also contribute to the larger cosmic web, the intricate network of galaxies and dark matter that spans the universe. By regulating the flow of gas and energy within their host galaxies, these black holes help determine how galaxies grow and evolve over billions of years. They can even influence the formation of galaxy clusters, the largest structures in the universe, by affecting the way galaxies interact and merge. What's truly remarkable is how these distant black holes, despite being billions of light years away, leave a lasting imprint on the cosmos. They remind us that the universe is a dynamic, interconnected system, where even the most distant objects can have a profound impact on the world around them. As we continue to study these cosmic giants, we gain not only a deeper understanding of black holes themselves, but also of the intricate dance between galaxies, stars, and the forces that shape our universe. Next, we'll explore the mystery of how supermassive black holes, especially those in the distant universe, grow to such enormous sizes, a question that continues to puzzle astronomers and challenges our understanding of cosmic evolution. Now, let's unravel one of the most perplexing mysteries in astrophysics: how supermassive black holes, particularly those in the distant universe, grow to such staggering sizes. These cosmic behemoths, often weighing billions of times the mass of our Sun, defy our expectations and challenge our understanding of the universe's early days. How do they become so massive, and what processes fuel their growth over billions of years? One leading theory suggests that supermassive black holes grow through a combination of mergers and accretion. In the early universe, smaller black holes likely formed from the collapse of massive stars. Over time, these black holes merged with one another, combining their masses to create larger and larger objects. This process of merging could have been accelerated in the dense environments of young galaxies, where black holes were more likely to encounter one another. But mergers alone can't fully explain the immense size of distant supermassive black holes. There's another critical factor at play: accretion. Accretion is the process by which black holes consume surrounding gas, dust, and even stars. As material spirals into the black hole, it forms an accretion disk, heating up and releasing tremendous amounts of energy. This energy not only makes the black hole visible across vast distances, but also provides the fuel for its growth. In the distant universe, where galaxies were rich in gas and dust, supermassive black holes had an almost endless supply of material to feed on. This rapid consumption allowed them to grow to enormous sizes in a relatively short period of time, at least on a cosmic scale. But here's where the mystery deepens. Observations of distant quasars, bright, energetic objects powered by supermassive black holes, reveal that some of these black holes were already billions of times the mass of the Sun when the universe was less than 1 billion years old. This raises a critical question: how did they grow so massive so quickly? One possibility is that the first black holes formed from the direct collapse of massive gas clouds, bypassing the star stage entirely. These seed black holes could have started out much larger than those formed from collapsing stars, giving them a head start in the race to become supermassive. Another intriguing idea involves the role of dark matter. Some scientists speculate that dark matter, which makes up most of the universe's mass, could have played a role in accelerating the growth of early black holes. By concentrating in dense regions, dark matter might have provided the gravitational pull needed to funnel gas and dust into these growing black holes at an unprecedented rate. While this remains a speculative theory, it highlights the complexity of the problem and the need for further research. The mystery of supermassive black holes isn't just about their size, it's about understanding the conditions of the early universe. These cosmic giants serve as time capsules, preserving clues about the environment in which they formed and grew. By studying them, we're not only uncovering the secrets of black holes, but also piecing together the story of how galaxies and the universe itself evolved. Next, we'll explore how gravitational lensing, a fascinating phenomenon predicted by Einstein's theory of relativity, helps astronomers study these distant black holes and the unique distortions they create in the fabric of space-time. Now, let's shift our focus to a phenomenon that sounds like it's straight out of science fiction, but is very much a reality: gravitational lensing. This incredible effect, predicted by Einstein's theory of general relativity, has become one of the most powerful tools astronomers use to study distant black holes. But what exactly is gravitational lensing, and how does it help us peer into the depths of the universe? Gravitational lensing occurs when a massive object, like a black hole or a galaxy, warps the fabric of space-time around it. This warping acts like a cosmic magnifying glass, bending the light from objects behind it and creating distorted or magnified images. Imagine looking through a glass of water and seeing the world beyond it twisted and stretched. That's a simplified version of what happens on a cosmic scale with gravitational lensing. For distant black holes, this effect is invaluable. It allows us to observe them in ways that would otherwise be impossible, given their immense distance and the faintness of their light. One of the most fascinating aspects of gravitational lensing is how it reveals the presence of black holes that might otherwise remain hidden. When light from a distant quasar or galaxy passes near a black hole, the black hole's immense gravity bends the light, creating multiple images or even a ring-like structure known as an Einstein ring. These distortions not only confirm the existence of the black hole, but also provide crucial information about its mass and location. By analyzing these lensed images, astronomers can map the distribution of matter around the black hole and gain insights into its properties. But gravitational lensing doesn't just help us detect black holes, it also allows us to study their surroundings in extraordinary detail. For example, lensing can magnify the light from the accretion disks around distant black holes, making it possible to observe features that would otherwise be too small or faint to see. This magnification has led to groundbreaking discoveries, such as the detection of supermassive black holes in the early universe and the measurement of their growth rates over billions of years. Another remarkable application of gravitational lensing is its ability to probe the nature of dark matter. Since dark matter doesn't emit light, it's invisible to traditional telescopes. However, its gravitational effects can distort the light from background objects, revealing its presence and distribution. By studying how dark matter interacts with black holes and their host galaxies, scientists can piece together a more complete picture of how these cosmic giants form and evolve. Gravitational lensing also offers a unique way to test Einstein's theory of general relativity on cosmic scales. The precise way light bends around massive objects like black holes provides a natural laboratory for exploring the limits of our understanding of gravity. Any deviations from Einstein's predictions could hint at new physics, potentially revolutionizing our understanding of the universe. As we continue to explore the cosmos, gravitational lensing remains a vital tool in our quest to understand distant black holes and the mysteries they hold. It's a testament to the ingenuity of astronomers and the power of science to uncover the hidden secrets of the universe. Next, we'll dive into the immense energy output of these distant black holes and how their jets and radiation shape the cosmos around them. Now, let's turn our attention to one of the most awe-inspiring aspects of distant black holes: their staggering energy output. These cosmic powerhouses don't just sit quietly in the void. They unleash unimaginable amounts of energy that can shape entire galaxies and influence the universe on a grand scale. But what exactly powers this energy, and how does it manifest in the cosmos? At the heart of a distant black hole's energy output lies its accretion disk, a swirling maelstrom of gas, dust, and other matter spiraling inward at incredible speeds. As this material gets closer to the black hole, it heats up to millions of degrees, emitting intense radiation across the electromagnetic spectrum, from X-rays to radio waves. This process alone makes black holes some of the brightest objects in the universe, even from billions of light years away. But the energy doesn't stop there. Many distant black holes also produce powerful jets, narrow beams of particles and radiation that shoot out from their poles at nearly the speed of light. These jets can extend for thousands or even millions of light years, far beyond the boundaries of their host galaxies. The energy contained in these jets is so immense that it can outshine the combined light of every star in the galaxy they originate from. Imagine a cosmic lighthouse beaming energy across the universe with unimaginable force. These jets and radiation don't just travel through space unnoticed, they have profound effects on their surroundings. For instance, the energy from a black hole's jets can heat up the gas in intergalactic space, preventing it from cooling and collapsing to form new stars. This process, known as feedback, plays a crucial role in regulating the growth of galaxies. Without it, galaxies might grow too large too quickly, altering the balance of the universe as we know it. In some cases, the energy from distant black holes can even trigger star formation. When the jets collide with dense clouds of gas, they compress the material, creating the perfect conditions for new stars to ignite. It's a cosmic paradox. Black holes, often thought of as destructive forces, can also be creators, shaping the universe in ways we're only beginning to understand. The energy output of distant black holes also provides valuable clues about their formation and evolution. By studying the radiation and jets, astronomers can estimate the black hole's mass, spin, and rate of growth. These insights help us piece together the life cycle of black holes, from their birth in the early universe to their role in shaping the cosmos over billions of years. As we continue to explore the universe, the energy emitted by distant black holes remains a key area of study. It's a reminder of the incredible forces at work in the cosmos and the profound impact these enigmatic objects have on the fabric of reality. Next, we'll explore how distant black holes connect to one of the most fundamental events in the universe, the Big Bang. Now, let's journey back in time to one of the most pivotal moments in cosmic history, the Big Bang. Distant black holes, those enigmatic giants lurking billions of light years away, hold secrets that can help us unravel the mysteries of the universe's earliest moments. But how exactly do these cosmic behemoths connect to the birth of everything we know? The key lies in their age. Many of the most distant black holes we've discovered formed just a few 100 million years after the Big Bang, making them some of the oldest objects in the universe. By studying these ancient black holes, astronomers can peer into the conditions of the early universe, a time when galaxies were just beginning to take shape and the cosmos was a vastly different place. These black holes act like cosmic time capsules, preserving clues about the environment in which they formed. One of the most fascinating aspects of this connection is the role of primordial gas. In the early universe, the first black holes likely formed from the collapse of massive clouds of primordial gas material that had not yet been enriched by the heavy elements forged in stars. By analyzing the light and radiation emitted by distant black holes, scientists can trace the composition of this ancient gas, offering insights into the chemical makeup of the universe shortly after the Big Bang. Additionally, the growth of these early black holes provides clues about the density and distribution of matter in the young universe. The fact that supermassive black holes existed so soon after the Big Bang suggests that the early cosmos was far more dynamic and chaotic than we once thought. It challenges our understanding of how quickly structures like black holes and galaxies could form, pushing the boundaries of our knowledge about cosmic evolution. Distant black holes also help us test theories about the expansion of the universe. The light from these ancient objects has traveled across billions of light years, stretching and shifting as the universe expanded. By studying this light, astronomers can measure the rate of cosmic expansion over time, providing critical data to refine our understanding of dark energy and the fate of the universe. Perhaps most intriguingly, distant black holes may hold clues about the very nature of the Big Bang itself. Some theories suggest that black holes could be remnants of quantum fluctuations, tiny ripples in the fabric of space-time, that were amplified during the rapid expansion of the early universe. If true, these black holes could offer a direct link to the quantum origins of the cosmos, bridging the gap between the microscopic and the cosmic. As we continue to study these ancient black holes, we're not just learning about the universe as it is today, we're uncovering the story of how it all began. Next, we'll dive into the challenges astronomers face when trying to observe these distant cosmic giants and the incredible tools they use to overcome them. Now, let's shift our focus to the immense challenges astronomers encounter when trying to observe these distant black holes. Studying objects billions of light years away is no small feat, and the hurdles are as vast as the distances involved. One of the biggest obstacles is the sheer faintness of these black holes. The light they emit has traveled across the universe for billions of years, becoming incredibly dim by the time it reaches us. Detecting such faint signals requires some of the most advanced telescopes ever built, capable of capturing even the tiniest traces of light. Another major challenge is the interference caused by cosmic dust and gas. As light from distant black holes travels through space, it passes through clouds of interstellar material that can absorb or scatter the light, making it even harder to detect. This means astronomers often have to rely on specific wavelengths of light, like X-rays or infrared, which can penetrate these obstacles more effectively. But even then, the data can be noisy and difficult to interpret, requiring sophisticated algorithms and models to extract meaningful information. Time itself also poses a unique challenge. Because these black holes are so far away, we're essentially looking back in time, observing them as they were billions of years ago. This means we're seeing them in their early stages of formation and evolution, which can make it difficult to compare them to black holes closer to us. Understanding how these ancient black holes grew and influenced their surroundings requires piecing together a cosmic puzzle with incomplete and fragmented data. On top of all this, the universe's expansion adds another layer of complexity. As space stretches, the light from distant black holes gets redshifted, meaning its wavelength stretches and shifts toward the red end of the spectrum. This effect can make it harder to identify certain features in the light, such as specific chemical signatures, which are crucial for understanding the black hole's environments. Astronomers must account for this redshift when analyzing their observations, adding another step to an already intricate process. Despite these challenges, the rewards of studying distant black holes are immense. Each observation brings us closer to understanding the early universe and the forces that shaped it. Next, we'll explore the incredible tools and technologies that astronomers use to overcome these obstacles and unlock the secrets of the cosmos. Now, let's turn our attention to one of the most powerful tools in the astronomer's arsenal, X-ray telescopes. These incredible instruments are absolutely essential for detecting and studying distant black holes, and their unique capabilities allow us to peer into the most energetic and hidden corners of the universe. Unlike optical telescopes, which rely on visible light, X-ray telescopes are designed to capture high-energy X-rays emitted by some of the most extreme objects in space, including black holes. Distant black holes often reveal themselves through the intense X-rays they produce, especially when they're actively feeding on surrounding matter. As material spirals into a black hole, it heats up to millions of degrees, emitting X-rays in the process. These X-rays can travel vast distances, cutting through cosmic dust and gas that might obscure other forms of light. This makes X-ray telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's Neutron invaluable for spotting black holes that would otherwise remain hidden. One of the key advantages of X-ray telescopes is their ability to reveal the high-energy processes happening near black holes. For example, they can detect the X-rays emitted by the superheated gas in the accretion disk, the swirling ring of matter that forms around a black hole as it consumes material. By studying these X-rays, astronomers can learn about the black hole's mass, spin, and even the speed at which it's devouring its surroundings. This information is crucial for understanding how black holes grow and evolve over time. Another remarkable feature of X-ray telescopes is their ability to observe phenomena like black hole jets. These are narrow beams of particles and radiation that shoot out from the poles of some black holes at nearly the speed of light. X-ray telescopes can capture the high-energy emissions from these jets, providing insights into how they form and how they impact their surroundings. This is particularly important for studying distant black holes, as their jets can influence entire galaxies and even the intergalactic medium. Of course, building and operating X-ray telescopes comes with its own set of challenges. X-rays are absorbed by Earth's atmosphere, which means these telescopes must be launched into space to function effectively. Once in orbit, they require precise calibration and advanced technology to detect and analyze the faint X-ray signals from distant black holes. Despite these hurdles, the data they provide is unparalleled, offering a window into the most extreme environments in the universe. Thanks to X-ray telescopes, we've been able to uncover some of the most distant and mysterious black holes, shedding light on their role in shaping the cosmos. Next, we'll dive into another fascinating aspect of black holes: how time itself behaves differently near these cosmic giants, and what that means for our observations. Now, let's shift our focus to one of the most mind-bending aspects of black holes: time dilation. This phenomenon, predicted by Einstein's theory of general relativity, reveals how time itself behaves differently near these cosmic giants. Near a black hole, the immense gravitational pull warps not just space but also time, creating effects that challenge our everyday understanding of how time flows. Imagine you're observing a clock falling toward a black hole. From your perspective, far away from the black hole, the clock would appear to tick slower and slower as it gets closer to the event horizon, the point of no return. This is because the black hole's gravity stretches time, making it pass more slowly for objects near it compared to those farther away. This effect, known as gravitational time dilation, means that time near a black hole doesn't just slow down, it practically grinds to a halt at the event horizon. For distant black holes, this has profound implications for how we observe them. When we detect light or other signals from a black hole billions of light years away, we're essentially looking back in time. But because of time dilation, the signals we receive are also influenced by the extreme gravity near the black hole. For example, if a star is being torn apart by a black hole, the process might appear to us as if it's happening in slow motion. This distortion gives astronomers a unique opportunity to study the behavior of matter under extreme conditions, but it also adds a layer of complexity to interpreting the data. Time dilation also plays a role in understanding the life cycles of black holes. For instance, a black hole that formed shortly after the Big Bang might appear to us as if it's still in its early stages of growth, even though billions of years have passed in the rest of the universe. This effect helps us piece together the history of black holes and their role in shaping the cosmos. But time dilation isn't just a quirk of distant black holes. It has broader implications for our understanding of time itself. It shows us that time isn't a fixed, universal constant, but rather a flexible dimension that can be stretched and warped by gravity. This realization has revolutionized physics, leading to new insights into the nature of space-time and the fundamental laws of the universe. As we continue to explore the mysteries of black holes, time dilation reminds us just how strange and fascinating the cosmos can be. Next, we'll delve into another intriguing aspect of these cosmic giants, the role of black hole mergers and the gravitational waves they produce. Now, let's turn our attention to one of the most dramatic events in the cosmos, black hole mergers. When two black holes collide, they unleash ripples in the fabric of space-time known as gravitational waves. These waves, first predicted by Einstein over a century ago, were directly detected for the first time in 2015, opening a new window into the universe. But what makes mergers involving distant black holes so fascinating? When black holes merge, especially those billions of light years away, the energy released is staggering. Imagine two massive objects, each with a mass of millions or even billions of suns, spiraling toward each other at incredible speeds. As they get closer, their immense gravity distorts space-time, sending out waves that travel across the universe at the speed of light. These gravitational waves carry information about the black hole's masses, spins, and even the environment in which they formed. For distant black holes, this process is particularly intriguing. Because these mergers happened so long ago, the gravitational waves we detect today offer a glimpse into the early universe. They tell us about the conditions that existed when galaxies were just beginning to form and how black holes grew to such enormous sizes. For example, some distant mergers suggest that supermassive black holes may have formed through repeated collisions, growing larger with each merger. But gravitational waves do more than just reveal the history of black holes. They also help us test Einstein's theory of general relativity in extreme conditions. By studying the patterns of these waves, scientists can confirm whether the predictions of relativity hold true even in the most violent events in the universe. So far, every detection has matched Einstein's equations, but future observations of distant mergers could uncover new physics or even hints of phenomena we haven't yet imagined. What's more, black hole mergers play a crucial role in shaping the universe. The energy released during these collisions can influence the formation of galaxies and the distribution of matter across the cosmos. In some cases, the gravitational waves from a merger might even trigger the birth of new stars or alter the orbits of nearby objects. As we continue to detect more mergers, especially those involving distant black holes, we're piecing together a clearer picture of how these cosmic giants evolve and interact. Each collision is like a cosmic fingerprint, revealing secrets about the universe's past and its underlying laws. Next, we'll dive into another profound mystery, the concept of singularities and what lies at the very heart of a black hole. Now, let's venture into the enigmatic core of black holes, the singularity. At the very heart of every black hole lies a point of infinite density and zero volume, where the laws of physics as we know them break down completely. This is the singularity, a place where gravity becomes so intense that not even light can escape, and space and time cease to behave in ways we can comprehend. The concept of a singularity challenges our understanding of the universe. According to Einstein's theory of general relativity, when a massive star collapses under its own gravity, it compresses into an infinitely small point. But here's the catch: infinities don't exist in nature. They're mathematical constructs, and their appearance in physics often signals that our theories are incomplete. This is why singularities remain one of the greatest mysteries in science. What makes singularities even more perplexing is that they're hidden behind the event horizon, the boundary of a black hole beyond which nothing can escape. This means we can't directly observe them, and all our knowledge comes from theoretical models and indirect evidence. For instance, the behavior of matter and light near the event horizon gives us clues about the extreme conditions closer to the singularity, but the singularity itself remains shrouded in mystery. One of the biggest questions surrounding singularities is what happens to the matter that falls into them. Does it get crushed out of existence, or does it somehow survive in a state we can't yet imagine? Some theories suggest that singularities might be gateways to other universes or dimensions, while others propose that quantum mechanics could prevent the formation of a true singularity, replacing it with something entirely different. The mystery deepens when we consider the role of quantum physics. General relativity, which predicts singularities, doesn't account for quantum effects. Yet, at such small scales, quantum mechanics becomes crucial. Scientists are working to develop a theory of quantum gravity that can reconcile these two frameworks and provide a clearer picture of what happens at the center of a black hole. Until then, singularities remain a tantalizing puzzle, pushing the boundaries of human knowledge. As we continue to explore the universe's most distant black holes, the study of singularities offers a glimpse into the fundamental nature of reality. They remind us that even in the vastness of space, there are still profound questions waiting to be answered. Next, we'll explore another fascinating phenomenon, Hawking radiation, and how it might hold the key to understanding the ultimate fate of black holes. Now, let's shift our focus to a groundbreaking discovery that redefined our understanding of black holes, Hawking radiation. Proposed by physicist Stephen Hawking in the 1970s, this phenomenon suggests that black holes aren't entirely black after all. Instead, they emit a faint glow of radiation, slowly losing energy and mass over time. Hawking radiation arises from the strange interplay between quantum mechanics and gravity at the edge of a black hole's event horizon. According to quantum theory, empty space isn't truly empty. It's filled with pairs of particles and antiparticles that constantly pop into existence and annihilate each other. Near the event horizon, one of these particles can fall into the black hole while the other escapes, carrying away a tiny bit of the black hole's energy. Over unimaginably long timescales, this process causes the black hole to evaporate. For distant black holes, Hawking radiation holds profound implications. These cosmic giants, billions of light years away, are slowly but surely losing mass through this process. While the rate of evaporation is incredibly slow for supermassive black holes taking trillions upon trillions of years, it's a reminder that even the most dominant forces in the universe aren't eternal. What's particularly fascinating is how Hawking radiation connects to the ultimate fate of black holes. As a black hole loses mass, its temperature increases, causing it to radiate more intensely. In the final moments of its existence, a black hole would release a burst of energy, effectively disappearing from the universe. This raises intriguing questions about what happens to all the information that fell into the black hole, a puzzle known as the black hole information paradox. Hawking radiation also offers a unique window into the quantum nature of gravity. While general relativity describes black holes as objects with infinite density, quantum mechanics suggests that nothing in nature is truly infinite. Hawking's work bridges these two worlds, hinting at a deeper theory that unites gravity and quantum physics. As we study the universe's most distant black holes, Hawking radiation reminds us that even the darkest corners of space are governed by subtle yet profound physical laws. It's a testament to the enduring quest to unravel the mysteries of the cosmos. Next, we'll explore how distant black holes might be linked to one of the universe's most elusive forces, dark energy. Now, let's turn our attention to one of the most mysterious forces in the cosmos, dark energy. This enigmatic energy is believed to be driving the accelerated expansion of the universe, and intriguingly, distant black holes might hold clues to understanding its nature. Dark energy makes up about 68% of the universe's total energy content, yet its origins and properties remain one of the greatest puzzles in modern physics. While we know it causes the universe to expand faster over time, Its connection to black holes, especially those billions of light-years away, is still being explored. One compelling theory suggests that distant black holes could act as cosmic probes, helping us measure the effects of dark energy on the universe's large-scale structure. As black holes grow and interact with their surroundings, they influence the distribution of matter and energy in their host galaxies. By studying how these black holes evolve over billions of years, astronomers can trace the impact of dark energy on the expansion of space itself. Another fascinating idea is that black holes might store or interact with dark energy in ways we don't yet fully understand. Some researchers propose that the energy emitted by black holes, including Hawking radiation, could be linked to the mechanisms driving dark energy. While this remains speculative, it opens up exciting possibilities for uncovering the secrets of this elusive force. Distant black holes also provide a unique vantage point for observing the universe's expansion. Because these black holes are so far away, the light we see from them has traveled for billions of years, offering a snapshot of the universe at different stages of its history. By analyzing how the light from these black holes is stretched and distorted, scientists can measure how the rate of expansion has changed over time, shedding light on the role of dark energy. As we continue to study the universe's most distant black holes, their connection to dark energy could revolutionize our understanding of the cosmos. These cosmic giants might not only shape the galaxies around them, but also hold the key to unraveling one of the universe's deepest mysteries. Next, we'll dive into how distant black holes have shaped the universe over billions of years, influencing everything from galaxy formation to the birth of stars. Now, let's shift our focus to the profound influence distant black holes have had on the evolution of the cosmos. These colossal entities are not just passive observers in the universe, they are active architects shaping the very fabric of space and time over billions of years. At the heart of nearly every galaxy lies a supermassive black hole, and distant black holes are no exception. These cosmic giants play a crucial role in the formation and evolution of galaxies. As matter falls into a black hole, it releases immense amounts of energy, heating up the surrounding gas and dust. This process can trigger the formation of new stars, effectively turning black holes into cosmic nurseries. But their influence doesn't stop there. The powerful jets of energy and radiation emitted by black holes can also regulate star formation. In some cases, these jets can blow away the gas and dust needed to form stars, effectively putting a halt to star creation in certain regions of a galaxy. This delicate balance between creation and destruction is one of the ways black holes shape the structure of galaxies over time. Distant black holes also play a key role in the growth of galaxies through a process known as feedback. As black holes consume matter, they release energy that can heat up the surrounding environment, preventing gas from cooling and collapsing into new stars. This feedback mechanism helps regulate the growth of galaxies, ensuring they don't grow too large too quickly. Over billions of years, the interplay between black holes and their host galaxies has led to the diverse array of galaxies we see today. From spiral galaxies with their elegant arms to elliptical galaxies with their smooth, featureless shapes, black holes have left their mark on the universe in profound ways. As we peer deeper into the cosmos, studying these distant black holes allows us to trace the history of galaxy formation and evolution. By understanding how black holes have shaped the universe, we gain valuable insights into the processes that have governed the cosmos since its earliest days. Next, we'll explore the concept of black hole shadows and how they provide a unique window into the nature of these enigmatic objects. Now, let's turn our attention to one of the most fascinating visual phenomena in the cosmos, black hole shadows. These shadows are not just eerie silhouettes in space. They are powerful tools that allow us to peer into the very heart of black holes and uncover their secrets. A black hole shadow is essentially the dark region at the center of a black hole, surrounded by a glowing ring of light. This ring is formed by light bending around the black hole's intense gravitational pull, a phenomenon predicted by Einstein's theory of general relativity. The shadow itself is created because no light can escape from the black hole's event horizon, making it appear as a dark void against the bright background of swirling matter. The first ever image of a black hole shadow was captured in 2019 by the Event Horizon Telescope, a global network of radio telescopes. This groundbreaking image featured the supermassive black hole at the center of the galaxy M87, located 55 million light-years away. The image revealed a bright, fiery ring encircling the black hole's shadow, confirming decades of theoretical predictions and providing a stunning visual representation of these cosmic giants. But why are black hole shadows so important? They offer astronomers a unique way to study the properties of black holes, such as their size, shape, and spin. By analyzing the shadow and the surrounding ring of light, scientists can test the predictions of general relativity and explore the extreme conditions near a black hole's event horizon. These observations also help us understand how black holes interact with their surroundings, from the accretion disks of swirling matter to the powerful jets of energy they emit. The image of M87's black hole was a monumental achievement, but it's just the beginning. As technology advances, astronomers hope to capture even sharper images of black hole shadows, including those of distant black holes. These observations could reveal new insights into the formation and evolution of black holes, as well as their role in shaping the universe. Black hole shadows are more than just cosmic curiosities. They are windows into the most extreme environments in the universe. By studying them, we gain a deeper understanding of the forces that govern the cosmos and the mysterious objects that lie at its heart. Next, we'll dive into how supercomputers are revolutionizing our ability to simulate and study distant black holes, unlocking new possibilities for discovery. Now, let's shift our focus to the incredible role supercomputers play in unraveling the mysteries of distant black holes. These powerful machines are not just tools for crunching numbers. They are virtual laboratories that allow scientists to simulate the most extreme environments in the universe, environments that are impossible to recreate on Earth. Supercomputers are essential for modeling the complex behavior of black holes, especially those located billions of light-years away. By processing vast amounts of data and running intricate simulations, these machines help astronomers predict how black holes form, grow, and interact with their surroundings. For example, supercomputers can simulate the collision of two black holes, a cataclysmic event that produces gravitational waves ripples in space-time that were first detected in 2015. These simulations provide a detailed look at the dynamics of such collisions, helping scientists interpret the signals picked up by gravitational wave detectors like LIGO and Virgo. One of the most remarkable aspects of supercomputer simulations is their ability to recreate the accretion disks around black holes, the swirling rings of gas and dust that feed these cosmic giants. By simulating the turbulent motions and magnetic fields within these disks, researchers can better understand how black holes consume matter and launch powerful jets of energy into space. These jets, which can stretch for thousands of light-years, are some of the most energetic phenomena in the universe, and supercomputers help us uncover the mechanisms behind them. Supercomputers also play a crucial role in testing the predictions of Einstein's theory of general relativity under extreme conditions. For instance, they can simulate the behavior of light as it bends around a black hole, creating the stunning visual effects we see in black hole shadows. These simulations not only confirm theoretical predictions, but also reveal subtle deviations that could hint at new physics beyond our current understanding. As technology advances, supercomputers are becoming even more powerful, enabling scientists to simulate larger and more complex systems. This includes modeling the formation of supermassive black holes in the early universe, a process that remains one of the greatest mysteries in astrophysics. By combining these simulations with observations from telescopes and gravitational wave detectors, astronomers are piecing together the story of how black holes shaped the cosmos over billions of years. Supercomputers are more than just tools. They are gateways to understanding the universe's most enigmatic objects. Through their simulations, we gain unprecedented insights into the behavior of distant black holes, bringing us closer to answering some of the biggest questions in science. Next, we'll explore another intriguing mystery, the black hole information paradox, and how distant black holes challenge our understanding of quantum mechanics. Now, let's dive into one of the most perplexing puzzles in modern physics, the black hole information paradox. This mystery strikes at the very heart of our understanding of quantum mechanics and the nature of reality itself. At its core, the paradox revolves around a simple yet profound question. What happens to information when it falls into a black hole? According to the laws of quantum mechanics, information cannot be destroyed. Every particle, every interaction leaves a trace, a kind of cosmic fingerprint that should, in theory, be preserved forever. But black holes, with their immense gravitational pull, seem to defy this principle. When matter falls into a black hole, it's thought to be crushed into a singularity, a point of infinite density where the laws of physics as we know them break down. If this is true, then the information about that matter would seemingly vanish, creating a direct conflict with quantum theory. This paradox becomes even more intriguing when we consider distant black holes. Because these black holes are billions of light years away, the light we observe from them today actually represents their state billions of years ago. This means that studying distant black holes gives us a glimpse into the early universe, where the rules of quantum mechanics and gravity were still shaping the cosmos. If information is truly lost in these ancient black holes, it could fundamentally alter our understanding of how the universe evolved. One proposed solution to the paradox is the idea of Hawking radiation, the process by which black holes slowly lose mass and energy over time. Stephen Hawking theorized that this radiation could carry away some of the information trapped within the black hole, effectively preserving it. However, this raises new questions. How exactly is the information encoded in the radiation, and can it ever be fully recovered? Another fascinating possibility is that information isn't lost at all, but instead stored on the black hole's event horizon, the boundary beyond which nothing can escape. This concept, known as the holographic principle, suggests that all the information about what falls into a black hole is encoded on its surface like a cosmic hard drive. If true, this would mean that black holes are not the destructive voids we once thought, but rather complex systems that preserve information in ways we're only beginning to understand. Distant black holes, with their immense size and age, provide a unique testing ground for these theories. By studying the light and radiation emitted by these ancient objects, scientists hope to uncover clues about how information behaves in the most extreme environments. Each observation brings us closer to resolving the paradox and perhaps to a deeper understanding of the fundamental laws that govern our universe. As we continue to explore this mystery, one thing is clear: the black hole information paradox is not just a theoretical curiosity. It's a gateway to uncovering the hidden connections between quantum mechanics, gravity, and the very fabric of space-time. Next, we'll turn our attention to the role of neutron stars and how they help us understand the formation of distant black holes. Now, shifting our focus to the cosmic dance between neutron stars and black holes, we uncover another layer of the universe's mysteries. Neutron stars, the incredibly dense remnants of massive stars that have exploded in supernova, play a crucial role in helping us understand how distant black holes form. These stellar corpses are so dense that a single teaspoon of neutron star material would weigh billions of tons on Earth. But what makes them particularly fascinating is their connection to black holes, especially those located billions of light years away. When a massive star exhausts its nuclear fuel, it collapses under its own gravity. If the core left behind is between about 1.4 and 3 times the mass of our Sun, it forms a neutron star. However, if the core is more massive than that, it continues collapsing until it becomes a black hole. This delicate balance between neutron stars and black holes provides astronomers with critical insights into the conditions required for black hole formation. By studying neutron stars, scientists can better understand the processes that lead to the birth of distant black holes, which often form in the early universe under extreme conditions. Neutron stars also serve as natural laboratories for testing the laws of physics under conditions that are impossible to replicate on Earth. For instance, the intense gravitational fields and magnetic forces around neutron stars mimic some of the environments near black holes. Observations of neutron stars, particularly those in binary systems where they orbit another star, have revealed how matter behaves under such extreme pressures. These findings help scientists predict how matter might behave as it spirals into a black hole, shedding light on the formation and growth of distant black holes. One of the most dramatic connections between neutron stars and black holes occurs when two neutron stars collide. These cataclysmic events, known as neutron star mergers, can produce gravitational waves that ripple through space-time, detectable by observatories like LIGO and Virgo. In some cases, these mergers result in the formation of a black hole. By studying these events, astronomers gain valuable clues about how black holes form in the distant universe, where similar mergers may have occurred billions of years ago. Moreover, neutron stars often emit powerful beams of radiation, known as pulsars, which can be detected across vast distances. These pulsars act as cosmic lighthouses, helping astronomers map the universe and locate regions where black holes might be forming. By combining observations of neutron stars with data from distant black holes, scientists can piece together a more complete picture of how these enigmatic objects evolve over time. As we continue to explore the relationship between neutron stars and black holes, one thing becomes clear: these celestial objects are deeply intertwined in the cosmic web. Neutron stars not only help us understand the mechanics of black hole formation, but also provide a window into the extreme physics that govern the universe. Next, we'll venture into the realm of theoretical physics as we explore the concept of wormholes and their potential connection to distant black holes. Now, let's take a leap into the realm of theoretical physics, where the boundaries of space and time blur, and the concept of wormholes emerges as one of the most intriguing ideas in modern science. Wormholes, often depicted in science fiction as shortcuts through the fabric of the universe, are hypothetical tunnels that could connect two distant points in space-time. While they remain purely theoretical, their potential connection to black holes, especially those located billions of light years away, opens up fascinating possibilities for understanding the universe. At their core, wormholes are solutions to the equations of Einstein's theory of general relativity. These equations suggest that under certain extreme conditions, space-time could fold in on itself, creating a bridge between two separate regions. Imagine space-time as a sheet of paper. If you fold the paper so that 2 points touch, a wormhole would be like a tunnel piercing through the fold, allowing for instantaneous travel between those points. While this sounds like something straight out of a sci-fi movie, the math behind it is grounded in real physics. But how do wormholes connect to distant black holes? One theory suggests that the intense gravitational fields of black holes could create the conditions necessary for wormholes to form. In fact, some scientists speculate that the singularity at the center of a black hole, a point where gravity becomes infinite and the laws of physics break down, might serve as one end of a wormhole. If this were true, it could mean that black holes are not just cosmic vacuum cleaners but potential gateways to other parts of the universe, or even other universes entirely. However, there's a catch. Wormholes, as theorized, are incredibly unstable. Without some form of exotic matter, a hypothetical substance with negative energy, to hold them open, they would collapse almost instantly. This makes the idea of traversable wormholes a significant challenge, even for advanced civilizations. Yet, the possibility that distant black holes could be linked to wormholes offers a tantalizing glimpse into how the universe might be interconnected on a scale far beyond our current understanding. Interestingly, the study of wormholes also ties back to the concept of quantum entanglement, where particles can be instantaneously connected across vast distances. Some physicists have proposed that wormholes could be the physical manifestation of this phenomenon, bridging the gap between quantum mechanics and general relativity. While this remains speculative, it highlights how distant black holes and wormholes could be part of a larger cosmic puzzle, one that challenges our understanding of space, time, and reality itself. As we ponder the mysteries of wormholes and their potential connection to distant black holes, we're reminded of how much we still have to learn about the universe. These theoretical structures, while not yet proven, inspire us to push the boundaries of science and imagination. Next, we'll explore another mind-bending idea: the role of black holes in the theoretical possibility of time travel. Now, shifting our focus to another mind-bending concept, let's explore the theoretical possibility of time travel and how black holes, particularly those located billions of light-years away, might play a role in this fascinating idea. Time travel has long been a staple of science fiction, but could it actually be rooted in real science? The answer lies in the extreme conditions surrounding black holes, where the laws of physics as we know them begin to break down. One of the key ideas linking black holes to time travel comes from Einstein's theory of general relativity. According to this theory, massive objects like black holes warp the fabric of space-time, creating what we perceive as gravity. Near a black hole, this warping becomes so intense that time itself slows down relative to an observer far away. This phenomenon, known as time dilation, means that if you were to hover near the edge of a black hole's event horizon, time for you would pass much more slowly than for someone on Earth. In theory, this could allow for a form of time travel into the future, as you would age slower compared to those outside the black hole's influence. But what about traveling to the past? This is where things get even more speculative. Some theories suggest that the extreme gravitational fields of black holes could create closed time-like curves, paths through space-time that loop back on themselves. If such curves exist, they could theoretically allow for travel back in time. However, this idea remains highly controversial and is not supported by any direct evidence. The conditions required to create these curves are so extreme that they may only exist in the realm of mathematical equations, not in the physical universe. Distant black holes add another layer of intrigue to this discussion. Because these black holes are located billions of light-years away, the light we see from them today actually represents their state billions of years ago. This means that studying distant black holes is, in a sense, like looking back in time. If we could somehow harness the properties of these ancient black holes, could they serve as portals to the past? While this remains purely speculative, it's a tantalizing thought that highlights the deep connection between black holes and the nature of time. Of course, the challenges of time travel are immense. Even if the physics allowed for it, the energy requirements and technological hurdles would be beyond anything humanity has ever achieved. And let's not forget the paradoxes that time travel introduces, such as the famous grandfather paradox, where traveling back in time could create contradictions that defy logic. Still, the study of black holes and their potential role in time travel pushes the boundaries of our understanding, reminding us that the universe is far stranger and more complex than we can imagine. As we ponder these possibilities, we're reminded that black holes are not just cosmic curiosities, they're windows into the deepest mysteries of space, time, and reality itself. Next, we'll dive into another intriguing concept, the mystery of white holes and their potential connection to distant black holes. Now, let's turn our attention to a concept that feels like it's straight out of science fiction: white holes. While black holes are known for their immense gravitational pull, trapping everything that crosses their event horizon, white holes are theorized to be their exact opposite. Imagine a cosmic object that doesn't pull matter in but instead expels it outward like a fountain of energy and light. This is the idea behind white holes, and while they've never been observed, they remain a fascinating topic in theoretical physics. So, what exactly is a white hole? In simple terms, it's a hypothetical region of space-time where matter and energy can only escape, never enter. Think of it as the reverse of a black hole. While black holes are like cosmic vacuum cleaners, white holes would be more like cosmic fire hoses, spewing out material and radiation. The concept arises from the equations of general relativity, which describe both black holes and white holes as solutions to the same set of equations. But while black holes are well supported by observational evidence, white holes remain purely theoretical. One of the most intriguing aspects of white holes is their potential connection to black holes. Some theories suggest that a white hole could be the other end of a black hole, connected by a theoretical tunnel known as a wormhole. In this scenario, matter that falls into a black hole could theoretically emerge from a white hole in another part of the universe, or even in another universe entirely. This idea ties into the concept of a bridge between 2 points in space-time, offering a possible explanation for how distant black holes might be linked to these mysterious white holes. But why haven't we detected white holes if they exist? One reason is that they're thought to be incredibly unstable. Unlike black holes, which can form from the collapse of massive stars, white holes would require conditions that are far more extreme and unlikely to occur naturally. Some physicists argue that white holes might only exist for a fraction of a second before collapsing or transforming into something else. Others suggest that they could be remnants of the early universe, relics from a time when the laws of physics were very different from what we observe today. Distant black holes add another layer of mystery to this discussion. If white holes do exist, they might be connected to the supermassive black holes we observe at the centers of galaxies, including those billions of light years away. These distant black holes, with their immense gravitational influence, could be the key to unlocking the secrets of white holes. By studying the behavior of black holes and the radiation they emit, scientists hope to find clues that might hint at the existence of these elusive cosmic objects. While the idea of white holes is still speculative, it's a reminder of how much we have yet to discover about the universe. They challenge our understanding of space, time, and the fundamental laws of physics, pushing us to think beyond what we can currently observe. As we continue to explore the mysteries of distant black holes, the possibility of white holes remains a tantalizing thought, inviting us to imagine what other wonders might be hidden in the cosmos. Next, we'll explore another fascinating concept, the role of black holes in multiverse theory and how distant black holes might provide evidence for alternate realities. Now, let's venture into one of the most mind-bending ideas in modern physics, the role of black holes in multiverse theory. Could these cosmic giants, especially the distant ones, hold clues to the existence of alternate realities? The concept of a multiverse suggests that our universe might be just one of many, each with its own unique set of physical laws and constants. And black holes, with their extreme gravitational forces and mysterious interiors, might just be the key to unlocking this cosmic puzzle. One intriguing idea is that black holes could act as gateways to other universes. According to some theories, the singularity at the center of a black hole, a point where gravity becomes infinite and space-time breaks down, might not be the end of the road. Instead, it could be a bridge to another universe, a connection between our reality and an entirely different one. This idea ties into the concept of wormholes, which we touched on earlier, but takes it a step further by suggesting that these tunnels could lead to parallel worlds. Distant black holes, in particular, add an extra layer of fascination to this theory. Because they are so far away, the light we see from them has traveled billions of years to reach us. This means we're observing them as they were in the distant past, potentially offering a glimpse into the early universe. If black holes do serve as portals to other realities, studying these ancient cosmic objects could provide evidence for the multiverse. For instance, unusual patterns in the radiation emitted by distant black holes might hint at interactions with other universes. Another angle comes from the study of black hole mergers. When two black holes collide, they create ripples in space-time known as gravitational waves. These waves carry information about the black hole's properties, and some scientists speculate that they might also carry traces of other universes. If a black hole in our universe were connected to one in another, the gravitational waves from a merger could reveal subtle anomalies that point to the existence of alternate realities. Of course, the multiverse theory is still highly speculative, and there's no direct evidence to prove it. But the idea that black holes, especially those billions of light years away, might hold the key to understanding the multiverse is a tantalizing possibility. It challenges us to rethink our understanding of space, time, and the very nature of reality. As we continue to study these distant cosmic phenomena, who knows what secrets they might reveal about the universe or universes we inhabit. Next, we'll explore how black holes bend and distort light, and how this phenomenon helps us study these enigmatic objects in even greater detail. Now, let's shift our focus to one of the most visually striking effects of black holes, their ability to bend and distort light. This phenomenon, known as gravitational lensing, is not just a fascinating cosmic spectacle, but also a powerful tool for studying distant black holes. When light passes near a black hole, its immense gravitational pull warps the fabric of space-time, causing the light to curve around it. This bending of light can create some truly mesmerizing effects, like multiple images of the same object or even a ring of light encircling the black hole, known as an Einstein ring. Gravitational lensing is particularly useful when it comes to observing distant black holes. Because these cosmic giants are so far away, their light is often too faint to detect directly. But when a black hole lies between us and a more distant object, like a galaxy or a quasar, its gravitational field can magnify and brighten the light from that object. This magnification acts like a natural telescope, allowing astronomers to study details that would otherwise be invisible. For example, by analyzing the distorted light from a background galaxy, scientists can map the distribution of matter around the black hole, including its accretion disk and any surrounding dark matter. But the impact of black holes on light goes beyond just magnification. The extreme conditions near a black hole can also stretch and twist light in ways that reveal its properties. For instance, as light spirals toward the event horizon, it gets stretched into longer, redder wavelengths, a process called redshift. This redshift provides crucial information about the black hole's mass and spin. Additionally, the way light is distorted can help us understand the shape and structure of the black hole's gravitational field, offering insights into how it interacts with its surroundings. One of the most famous examples of this is the first ever image of a black hole, captured by the Event Horizon Telescope in 2019. The image showed a bright ring of light surrounding a dark shadow, the black hole's event horizon. This ring is the result of light bending around the black hole, and its shape and brightness provided valuable data about the black hole's size and the behavior of matter near its edge. Without the ability to study how black holes distort light, such groundbreaking discoveries would be impossible. By observing these distortions, astronomers can also test some of the most fundamental predictions of Einstein's theory of general relativity. For example, the precise way light bends around a black hole can reveal whether our understanding of gravity holds true under such extreme conditions. Any deviations from the expected behavior could point to new physics, potentially reshaping our understanding of the universe. As we continue to explore the universe's most distant black holes, the way they interact with light will remain a cornerstone of our research. These cosmic lenses not only help us peer into the farthest reaches of space, but also deepen our understanding of the forces that shape it. Next, we'll dive into how black holes recycle matter and energy, and how this process contributes to the cosmic cycle of creation and destruction. Now, let's turn our attention to one of the most fascinating roles black holes play in the universe's cosmic recycling. Black holes aren't just destructive forces, they're also incredible recyclers of matter and energy, shaping the cosmos in ways that might surprise you. When matter falls into a black hole, it doesn't simply vanish. Instead, it gets transformed and redistributed, fueling new processes that ripple across the universe. At the heart of this recycling process is the black hole's accretion disk, a swirling vortex of gas, dust, and other matter spiraling toward the event horizon. As this material gets pulled in, it heats up to incredible temperatures, emitting vast amounts of energy in the form of light, X-rays, and even powerful jets of particles. These jets can shoot out at nearly the speed of light, carrying energy and matter far beyond the black hole itself. In this way, black holes act like cosmic power plants, converting matter into energy that can influence entire galaxies. But the recycling doesn't stop there. Some of the material in the accretion disk doesn't make it past the event horizon. Instead, it gets flung outward by intense magnetic fields and radiation pressure, creating outflows that can travel thousands of light years. These outflows carry heavy elements like carbon, oxygen, and iron, forged in the hearts of stars and supernova. When these elements are ejected into space, they become the building blocks for new stars, planets, and even life itself. In a sense, black holes are cosmic recyclers, turning the remnants of dead stars into the seeds of future worlds. Distant black holes play a particularly important role in this process. Because they are often located in the centers of galaxies, their outflows can spread across vast regions, enriching entire galactic neighborhoods with the raw materials needed for star formation. This recycling of matter and energy helps regulate the growth of galaxies, ensuring that they don't burn through their fuel too quickly. Without black holes, the universe might look very different. Star formation could slow down, and galaxies might not evolve in the same way. One of the most striking examples of this recycling can be seen in quasars, the incredibly bright cores of distant galaxies powered by supermassive black holes. Quasars emit so much energy that they can outshine entire galaxies, and their outflows can travel millions of light years, spreading elements far and wide. These outflows not only recycle matter but also help clear out regions of space, creating the conditions for new stars and galaxies to form. In this way, distant black holes are like cosmic gardeners, pruning and nurturing the universe on an unimaginable scale. As we continue to study these distant black holes, we're learning more about how they shape the cosmos. Their ability to recycle matter and energy is a testament to the interconnectedness of the universe, where even the most destructive forces can give rise to new beginnings. Next, we'll explore the mystery of intermediate black holes and their potential role in the formation of distant supermassive black holes. Now, let's shift our focus to one of the most intriguing mysteries in the study of black holes: intermediate black holes. These cosmic enigmas sit somewhere between the smaller stellar mass black holes, formed from collapsing stars, and the colossal supermassive black holes that dominate the centers of galaxies. Despite their importance, intermediate black holes have proven incredibly difficult to detect, leaving scientists with more questions than answers. Intermediate black holes are thought to have masses ranging from a few hundred to a few 100,000 times that of our Sun. This places them in a unique category, bridging the gap between the smaller and larger black holes we're more familiar with. But why are they so elusive? One reason is that they don't produce the same dramatic signals as their larger or smaller counterparts. Stellar mass black holes often reveal themselves through gravitational waves when they collide, while supermassive black holes are visible through the intense radiation emitted by their accretion disks. Intermediate black holes, however, tend to fly under the radar, making them a challenge to spot. Despite their elusiveness, intermediate black holes are believed to play a crucial role in the formation of supermassive black holes. One leading theory suggests that these intermediate black holes could act as building blocks, merging over time to create the supermassive giants we see today. Imagine a cosmic game of connect the dots where smaller black holes come together, growing larger and larger until they reach supermassive proportions. This process could explain how supermassive black holes formed so quickly in the early universe, a puzzle that has long baffled astronomers. Another fascinating aspect of intermediate black holes is their potential to influence star formation and galactic evolution. When they reside in dense star clusters, their gravitational pull can disrupt the orbits of nearby stars, sometimes even flinging them out of the cluster entirely. This dynamic interaction can shape the structure of galaxies, influencing where and how stars form. In this way, intermediate black holes might act as cosmic sculptors, quietly shaping the universe on a smaller scale before merging into something much larger. The search for intermediate black holes continues, with astronomers using a variety of techniques to track them down. One promising method involves looking for the telltale signs of stars orbiting an unseen object with the mass of an intermediate black hole. Another approach focuses on detecting the faint X-ray emissions that might be produced as these black holes consume nearby matter. Each new discovery brings us closer to understanding their role in the cosmic puzzle. As we unravel the mystery of intermediate black holes, we gain deeper insights into the formation and evolution of the universe's most distant and massive black holes. These elusive objects remind us that the cosmos is full of surprises, and even the quietest players can have a profound impact on the grand stage of the universe. Next, we'll explore how distant black holes often reside at the centers of galaxies and their impact on galactic dynamics. Now, let's turn our attention to the heart of galaxies, where distant black holes often take center stage. These supermassive black holes lurking at the cores of galaxies are not just passive observers. They are active players shaping the very fabric of their cosmic neighborhoods. Their immense gravitational influence can dictate the movement of stars, gas, and even entire star systems, making them key architects of galactic dynamics. At the center of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These colossal objects can weigh millions or even billions of times the mass of our Sun, and their presence is felt far beyond their event horizons. One of their most dramatic effects is their ability to regulate star formation. As gas and dust spiral toward the black hole, they form an accretion disk, heating up and emitting intense radiation. This radiation can either trigger the birth of new stars or, in some cases, blow away the raw materials needed for star formation, effectively putting a halt to the process. It's a delicate balance, and the black hole's activity can determine whether a galaxy becomes a bustling stellar nursery or a quiet, aging system. But the influence of these central black holes doesn't stop there. Their gravitational pull can also shape the orbits of stars and other objects within the galaxy. Stars that venture too close can be flung out into intergalactic space, while others may be drawn into tighter, faster orbits. This gravitational dance can create unique structures, such as tightly packed star clusters or elongated streams of stars, adding to the galaxy's overall complexity. In some cases, the black hole's activity can even trigger galactic collisions, as its gravitational pull draws neighboring galaxies closer together. Perhaps one of the most fascinating aspects of these central black holes is their role in powering some of the brightest objects in the universe, quasars. When a supermassive black hole consumes vast amounts of matter, it releases enormous amounts of energy, outshining entire galaxies. These quasars act as cosmic lighthouses, illuminating the distant reaches of the universe and providing astronomers with valuable insights into the early stages of galaxy formation. The relationship between supermassive black holes and their host galaxies is a dynamic and intricate one. They don't just reside at the center, they actively shape the galaxy's evolution, influencing everything from star formation to the galaxy's overall structure. As we continue to study these cosmic giants, we uncover more about how they contribute to the grand tapestry of the universe. Next, we'll explore how gamma-ray bursts are linked to distant black holes and what they reveal about these explosive cosmic events. Now, shifting our gaze to some of the most energetic events in the cosmos, let's dive into the fascinating connection between gamma-ray bursts and distant black holes. Gamma-ray bursts, or GRB, are among the most powerful explosions in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. But what do these colossal bursts of energy have to do with black holes? The answer lies in the dramatic processes that occur when massive stars collapse or when black holes merge. When a massive star reaches the end of its life, it doesn't go quietly. Instead, it undergoes a cataclysmic explosion known as a supernova. In some cases, the core of the star collapses into a black hole, and as this happens, jets of energy are launched outward at nearly the speed of light. These jets, packed with gamma rays, are what we observe as gamma-ray bursts. The sheer intensity of these bursts makes them visible across vast cosmic distances, allowing astronomers to study them even when they originate from the far reaches of the universe. But gamma-ray bursts aren't just linked to the birth of black holes, they can also occur when two black holes collide. When these massive objects spiral toward each other and merge, they release gravitational waves and in some cases produce jets of gamma rays. These bursts provide a unique window into the behavior of black holes, revealing details about their masses, spins, and the environments in which they exist. By studying GRBs, scientists can piece together the story of how black holes form, grow, and interact with their surroundings. One of the most intriguing aspects of gamma-ray bursts is their ability to act as cosmic probes. Because they are so bright, they can be detected from billions of light years away, offering a glimpse into the early universe. By analyzing the light from these bursts, astronomers can learn about the conditions of the universe when it was much younger, including the formation of the first stars and black holes. This makes GRBs not just spectacular cosmic fireworks, but also invaluable tools for understanding the history and evolution of the cosmos. The connection between gamma-ray bursts and distant black holes underscores the dynamic and interconnected nature of the universe. These bursts are more than just fleeting flashes of light, they are powerful messengers, carrying information about some of the most extreme events in space. As we continue to study them, we uncover new insights into the life cycles of stars, the behavior of black holes, and the evolution of the universe itself. Next, we'll explore how distant black holes influence the formation and evolution of stars, shaping the galaxies they call home. Now, let's turn our attention to one of the most fascinating dual roles black holes play in the cosmos, their ability to both create and destroy stars. It might sound contradictory, but distant black holes are cosmic architects, shaping the universe in ways that are as destructive as they are creative. When we think of black holes, destruction often comes to mind: swallowing stars, tearing apart matter, and bending space-time to its will. And yes, black holes are incredibly destructive. When a star ventures too close to a supermassive black hole, the immense gravitational forces can rip it apart in a process called tidal disruption. This violent event not only destroys the star but also releases a burst of energy that can be observed across the universe. But here's where it gets interesting. Black holes aren't just cosmic wrecking balls, they're also star factories. In the swirling disks of gas and dust that surround supermassive black holes, conditions can become just right for star formation. As material spirals inward, it heats up and creates intense pressure. In some regions, this pressure triggers the collapse of gas clouds, leading to the birth of new stars. These stars form in the most unlikely of places, right in the shadow of a black hole's immense gravity. This dual role of black holes has profound implications for the evolution of galaxies. By destroying stars, black holes regulate the amount of material available for future star formation. But by creating stars, they contribute to the growth and structure of galaxies, seeding them with new stellar populations. Over billions of years, this cycle of creation and destruction shapes the universe, influencing how galaxies form, evolve, and interact with one another. What's even more remarkable is how this process connects distant black holes to the broader story of the cosmos. The stars born near black holes can go on to form planetary systems, potentially hosting worlds that might one day harbor life. Meanwhile, the destruction of stars feeds the black hole, allowing it to grow and continue its influence on its galactic environment. In essence, black holes are not just passive observers of the universe, they are active participants, driving the cycles of star formation and destruction that define the cosmos. As we continue to study these distant giants, we uncover more about how they shape the universe, from the smallest stars to the largest galaxies. Next, we'll delve into the mystery of primordial black holes and their potential role in the early universe. Now, let's shift our gaze to one of the most intriguing theories in astrophysics, the mystery of primordial black holes. Unlike the black holes we've discussed so far, which form from the collapse of massive stars or the merging of smaller black holes, primordial black holes are thought to have emerged in the very early moments of the universe. These ancient cosmic objects, if they exist, could hold the key to understanding some of the deepest questions about the cosmos. Primordial black holes are believed to have formed not from stars, but from the extreme density fluctuations in the universe's infancy, just fractions of a second after the Big Bang. Imagine the universe as a bubbling, chaotic soup of energy and matter. In some regions, the density was so intense that pockets of space collapsed under their own gravity, forming black holes. These primordial black holes could range in size from as small as an atom to as massive as thousands of suns, making them a fascinating and diverse class of objects. What makes primordial black holes so captivating is their potential to solve some of the universe's greatest mysteries. For instance, they are a leading candidate for dark matter, the invisible substance that makes up a significant portion of the universe's mass. If primordial black holes exist in large numbers, they could account for the gravitational effects we observe in galaxies and galaxy clusters, effects that cannot be explained by visible matter alone. This would mean that these ancient black holes have been silently shaping the universe since its earliest days. Another tantalizing possibility is that primordial black holes could help us understand the nature of the Big Bang itself. By studying these relics of the early universe, scientists might uncover clues about the conditions that prevailed during the universe's birth. Some theories even suggest that primordial black holes could have played a role in the formation of the first stars and galaxies, acting as seeds around which matter gathered and collapsed. Despite their potential significance, primordial black holes remain elusive. Detecting them is a monumental challenge because they don't emit light or radiation like other black holes. However, astronomers have proposed creative methods to search for them, such as looking for the gravitational lensing effects they might produce or observing the ripples they could create in the cosmic microwave background, the afterglow of the Big Bang. The search for primordial black holes is a reminder of how much we still have to learn about the universe. If they exist, they could rewrite our understanding of cosmic history, dark matter, and the very fabric of space and time. As we continue to explore the distant reaches of the cosmos, the mystery of primordial black holes remains one of the most compelling puzzles waiting to be solved. Next, we'll explore how distant black holes contribute to the structure of the cosmic web, the vast network that connects the universe on the largest scales. Now, let's unravel one of the most fascinating roles distant black holes play in the universe shaping the cosmic web. Picture the universe not as a random scattering of galaxies, but as an intricate, interconnected network, like a spider's web stretching across unimaginable distances. This vast structure, known as the cosmic web, is the backbone of the universe, and distant black holes are some of its most influential architects. At the heart of this cosmic web are supermassive black holes, often found at the centers of galaxies. These colossal objects don't just sit quietly, they actively shape their surroundings. As matter falls into a black hole, it releases enormous amounts of energy, heating up the surrounding gas and influencing how galaxies form and evolve. This process, known as feedback, can trigger the birth of new stars or, conversely, halt star formation altogether. Over billions of years, these interactions help weave the threads of the cosmic web, connecting galaxies and galaxy clusters in a delicate balance of gravity and energy. But how exactly do distant black holes contribute to this grand structure? One key way is through their gravitational pull. Black holes, especially supermassive ones, exert a powerful influence on their surroundings. They can pull in nearby matter, creating dense regions where galaxies cluster together. At the same time, the energy they release can push matter away, carving out vast voids in the cosmic web. This interplay between attraction and repulsion helps define the web's intricate pattern of filaments and empty spaces. Another critical role black holes play is in the formation of galaxy clusters, the largest structures in the universe. These clusters are like cities of galaxies bound together by gravity. Distant black holes, through their immense gravitational influence and energetic feedback, help regulate the growth of these clusters. They act as cosmic anchors, drawing galaxies together while also influencing the distribution of dark matter, the invisible scaffolding that holds the cosmic web together. The cosmic web isn't just a static structure, it's dynamic, constantly evolving over billions of years. Distant black holes, with their ability to shape galaxies and influence the flow of matter, are key players in this ongoing cosmic dance. By studying how these black holes interact with their surroundings, scientists can piece together the story of how the universe grew from a smooth, uniform state after the Big Bang into the complex, web-like structure we see today. As we continue to explore the universe's most distant black holes, we gain deeper insights into their role in shaping the cosmic web. These enigmatic objects are not just isolated phenomena, they are integral to the universe's large-scale structure, connecting galaxies, clusters, and voids in a vast, interconnected network. Next, we'll dive into the intriguing connection between distant black holes and quantum entanglement, a phenomenon that challenges our understanding of physics itself. Now, let's venture into one of the most mind-bending aspects of distant black holes, their potential connection to quantum entanglement. At first glance, black holes and quantum mechanics might seem like entirely separate realms of physics. One deals with the immense gravitational forces of the universe's most massive objects, while the other explores the strange, counterintuitive behavior of particles at the smallest scales. But what if these two worlds are more connected than we ever imagined? Quantum entanglement is a phenomenon where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, defies our everyday understanding of space and time. Now, imagine this concept applied to black holes. Some theories suggest that the information swallowed by a black hole might not be lost forever but could instead be entangled with particles outside the black hole. This idea has led scientists to propose that black holes could be connected to each other through quantum entanglement, forming a kind of cosmic network. But here's where things get even more intriguing. The concept of entanglement between black holes challenges our understanding of space-time itself. According to some theories, entangled black holes could create wormholes, hypothetical tunnels through space-time that connect distant points in the universe. These wormholes, also known as Einstein-Rosen bridges, could provide a way for information to travel between black holes, even if they are billions of light years apart. This idea blurs the line between quantum mechanics and general relativity, two of the most fundamental but seemingly incompatible theories in physics. The implications of this connection are profound. If black holes are entangled, it could mean that the universe is far more interconnected than we ever realized. It might even hint at a deeper, underlying structure to reality, one where space and time are not the fixed, unchanging backdrop we perceive, but are instead dynamic and woven together by quantum links. This could revolutionize our understanding of everything from the nature of gravity to the origins of the universe itself. However, studying this connection is no easy task. The extreme conditions near black holes and the elusive nature of quantum entanglement make it incredibly challenging to test these ideas experimentally. Yet, advancements in theoretical physics and observational tools are bringing us closer to uncovering the truth. By exploring the potential link between distant black holes and quantum entanglement, scientists are pushing the boundaries of our knowledge, challenging long-held assumptions, and opening up new frontiers in our quest to understand the cosmos. As we continue to unravel these mysteries, one thing is clear: the universe is far stranger and more interconnected than we ever imagined, and distant black holes, with their immense gravitational pull and enigmatic behavior, are at the heart of this cosmic puzzle. Next, we'll explore how these black holes might influence the expansion of the universe and the role of dark energy in shaping its fate. Now, let's shift our focus to one of the most profound questions in cosmology: how distant black holes might play a role in the expansion of the universe. At first glance, black holes seem like cosmic vacuum cleaners, pulling everything into their gravitational grip. But could they also be influencing the very fabric of the universe on a much larger scale? The answer lies in the mysterious force known as dark energy, which is driving the accelerated expansion of the cosmos. Dark energy makes up about 68% of the universe, and it's the reason why galaxies are moving away from each other at ever-increasing speeds. But here's where black holes come into the picture. Some theories suggest that the immense gravitational fields of supermassive black holes, especially those in distant galaxies, could interact with dark energy in ways we're only beginning to understand. These black holes, often found at the centers of galaxies, might act as cosmic anchors, shaping the flow of dark energy and influencing how the universe expands over time. One intriguing idea is that black holes could be contributing to the overall energy density of the universe. As they grow by consuming matter and merging with other black holes, they release enormous amounts of energy in the form of gravitational waves and radiation. This energy could subtly affect the balance of dark energy, potentially altering the rate of cosmic expansion. While this connection is still theoretical, it opens up fascinating possibilities for understanding how black holes and dark energy work together to shape the fate of the universe. Another angle to consider is the role of black holes in the large-scale structure of the cosmos. The distribution of black holes across the universe might influence how dark energy behaves on a grand scale. For instance, regions with dense clusters of black holes could create local variations in the expansion rate, leading to a more complex and dynamic universe than we currently imagine. This interplay between black holes and dark energy could help explain some of the anomalies observed in the cosmic microwave background, the afterglow of the Big Bang. Of course, studying this connection is no small feat. The extreme distances and faint signals from distant black holes make it incredibly challenging to gather direct evidence. However, advancements in telescopes and observational techniques are bringing us closer to uncovering these cosmic secrets. By combining data from gravitational wave detectors, X-ray telescopes, and other instruments, scientists are piecing together a more complete picture of how black holes and dark energy interact. As we continue to explore this cosmic dance, one thing becomes clear. Black holes are not just isolated objects lurking in the darkness of space. They are active participants in the grand story of the universe, shaping its structure, influencing its expansion, and challenging our understanding of the forces that govern it. Next, we'll dive into the mystery of black hole spin and how it affects their behavior, shedding light on yet another fascinating aspect of these cosmic giants. Now, let's turn our attention to one of the most intriguing aspects of black holes, their spin. Just like planets and stars, black holes can rotate, and this spin plays a crucial role in shaping their behavior and the environment around them. But what exactly does the spin of a black hole tell us, especially when it comes to those located billions of light years away? The spin of a black hole is determined by the angular momentum of the material that formed it. When a massive star collapses, it doesn't just vanish into a static point. It carries with it the momentum of its rotation. This means that as the star's core collapses, its spin speeds up, much like a figure skater pulling in their arms to spin faster. The result is a black hole that can rotate at incredible speeds, sometimes approaching the speed of light. But why does this matter? The spin of a black hole influences how it interacts with its surroundings. For instance, a rapidly spinning black hole can drag space-time around it, a phenomenon known as frame dragging. This creates a swirling effect that can accelerate nearby matter, leading to the formation of powerful jets of energy and radiation. These jets, often observed in distant quasars, are some of the most energetic phenomena in the universe, and they're directly linked to the spin of the black hole at their center. The spin also provides clues about the black hole's history. A black hole with a high spin rate likely formed from the collapse of a single massive star or grew by consuming material in a consistent direction, allowing its spin to build up over time. On the other hand, a black hole with a slower spin might have formed through chaotic processes, such as the collision and merger of multiple black holes, which can cancel out some of the angular momentum. Studying the spin of distant black holes is no easy task because they're so far away their signals are faint and often obscured by intervening matter. However, astronomers use a combination of X-ray observations and computer simulations to measure the spin indirectly. By analyzing the way light bends and shifts near the black hole's event horizon, they can estimate how fast it's rotating. These measurements not only reveal the black hole's spin, but also provide insights into the conditions that led to its formation billions of years ago. The spin of black holes also has implications for our understanding of the universe's evolution. Rapidly spinning black holes are more efficient at converting matter into energy, which means they can have a greater impact on their host galaxies. This energy output can influence star formation, galactic winds, and even the distribution of dark matter. By studying the spin of distant black holes, scientists can piece together how these cosmic giants have shaped the universe over billions of years. As we continue to unravel the mysteries of black hole spin, one thing is certain: these rotating behemoths are far more dynamic than we once thought. They're not just static points of gravity, they're active, spinning engines that drive some of the most dramatic processes in the cosmos. Next, we'll explore how black holes regulate the growth of galaxies through a process known as cosmic feedback, shedding light on yet another fascinating aspect of their role in the universe. Now, shifting our focus to another fascinating aspect of black holes, let's explore how these cosmic giants play a crucial role in regulating the growth of galaxies through a process known as cosmic feedback. This phenomenon is one of the most important ways black holes influence their surroundings, shaping the evolution of galaxies over billions of years. Cosmic feedback occurs when the energy and radiation emitted by a black hole interact with the surrounding gas and dust in its host galaxy. This interaction can have profound effects, either heating up the gas to prevent it from collapsing into new stars or, in some cases, triggering star formation by compressing the gas. It's a delicate balance, and black holes are the ultimate regulators. One of the key mechanisms of cosmic feedback is through the powerful jets of energy that many black holes produce. These jets, often fueled by the black hole's spin and accretion disk, can travel vast distances, pushing gas and dust out of the galaxy's central regions. This process, known as outflow, can effectively starve the galaxy of the raw materials needed to form new stars, slowing down its growth. On the other hand, when these jets collide with surrounding gas clouds, they can create shock waves that compress the gas, leading to bursts of star formation in other parts of the galaxy. Another important aspect of cosmic feedback is the radiation emitted by the black hole's accretion disk. As matter spirals into the black hole, it heats up and releases enormous amounts of energy, including X-rays and ultraviolet light. This radiation can ionize the surrounding gas, making it too hot to collapse and form stars. In this way, black holes act as cosmic thermostats, controlling the temperature and density of the gas in their galaxies. Interestingly, cosmic feedback isn't just a one-way street. The growth of the black hole itself is influenced by the availability of gas in its host galaxy. When a galaxy has plenty of gas, the black hole can grow rapidly, consuming material and releasing energy that regulates the galaxy's evolution. But as the black hole's feedback mechanisms kick in, they can reduce the amount of available gas, slowing down both the black hole's growth and the galaxy's star formation. This creates a self-regulating cycle that shapes the destiny of galaxies over cosmic time. Studying distant black holes gives us a unique window into this process. Because the light we observe from these black holes has traveled billions of years to reach us, we're essentially looking back in time, seeing how black holes influenced galaxies in the early universe. This helps scientists understand how galaxies evolved from their chaotic beginnings into the structured systems we see today. The role of black holes in cosmic feedback is a testament to their power and influence. They're not just passive objects lurking in space, they're active participants in the life cycle of galaxies, shaping their growth and evolution in ways we're only beginning to understand. Next, we'll delve into how black holes might even influence the formation and evolution of exoplanets, adding yet another layer to their cosmic significance. Now, let's turn our attention to an intriguing connection that ties distant black holes to the worlds beyond our solar system, exoplanets. While black holes are often seen as destructive forces, their influence extends far beyond their immediate surroundings, potentially shaping the birth and evolution of planets in their host galaxies. Distant black holes, especially supermassive ones, can have a profound impact on the environments of their galaxies. The energy and radiation they emit can heat up or compress gas clouds, creating conditions that either hinder or promote the formation of stars and, by extension, the planets that orbit them. This means that black holes, despite their reputation, might play a surprising role in the creation of exoplanets. One way this happens is through the jets of energy that many black holes produce. These jets can travel vast distances, interacting with gas clouds and triggering shock waves. When these shock waves compress gas, they can lead to the formation of new stars, and where there are stars, there's the potential for planets to form. In this way, black holes can act as cosmic catalysts, indirectly influencing the birth of exoplanets. But the story doesn't end there. The radiation emitted by black holes, particularly X-rays and ultraviolet light, can also affect the chemical composition of the gas in their galaxies. This radiation can ionize gas, breaking apart molecules and altering the conditions needed for planet formation. In some cases, this might prevent planets from forming altogether, while in others, it could create unique environments that lead to the formation of planets with unusual characteristics. Interestingly, the gravitational pull of a supermassive black hole can also influence the orbits of stars and planets within its galaxy. Over time, this gravitational influence can cause stars and their planetary systems to migrate, bringing them closer to or farther from the galactic center. This movement can expose planets to different levels of radiation and gravitational forces, potentially affecting their atmospheres, climates, and even their ability to support life. Studying distant black holes gives us a glimpse into how these processes unfolded in the early universe. By observing black holes billions of light years away, we're essentially looking back in time, seeing how they influenced the formation of stars and planets in their galaxies. This helps scientists piece together the complex puzzle of how galaxies and their planetary systems evolved over billions of years. The connection between black holes and exoplanets is a reminder of how interconnected the universe truly is. Even the most distant and seemingly isolated objects can have far-reaching effects, shaping the cosmos in ways we're only beginning to understand. Next, we'll explore how collisions between galaxies and black holes, especially distant ones, continue to shape the universe in dramatic and unexpected ways. Now, let's dive into the dramatic and chaotic world of cosmic collisions, where galaxies and black holes collide in some of the most energetic events in the universe. These collisions are not just spectacular to observe, they also play a crucial role in shaping the cosmos as we know it. When galaxies collide, their supermassive black holes often take center stage. These black holes, which reside at the centers of galaxies, can be millions or even billions of times more massive than our Sun. As galaxies merge, their black holes begin to orbit each other, eventually spiraling closer and closer until they collide. This process releases an enormous amount of energy in the form of gravitational waves, ripples in space-time that were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. But the collision of black holes doesn't just create gravitational waves, it can also trigger a chain reaction of cosmic events. The immense energy released during these mergers can heat up surrounding gas, sparking bursts of star formation. In some cases, the collision can even eject stars and gas from the newly formed galaxy, creating long streams of material that stretch across space. Distant black holes, in particular, offer a unique window into these processes. Because light takes time to travel across the universe, observing black holes billions of light years away allows us to see how these collisions unfolded in the early universe. This helps scientists understand how galaxies and their black holes evolved over time, growing larger and more complex through repeated mergers. Interestingly, these collisions can also lead to the formation of even more massive black holes. When two supermassive black holes merge, the resulting black hole can be significantly larger than either of its predecessors. This process helps explain how some of the most massive black holes in the universe, like those found in the centers of giant elliptical galaxies, came to be. But the impact of these collisions goes beyond just black holes and galaxies. The gravitational waves produced by these events carry information about the nature of space-time itself, providing insights into fundamental physics. By studying these waves, scientists can test theories about gravity, black holes, and the structure of the universe. Cosmic collisions remind us that the universe is a dynamic and ever-changing place. From the birth of new stars to the creation of supermassive black holes, these events shape the cosmos in profound and lasting ways. Next, we'll explore the mysterious and powerful jets that some black holes produce, and how they help us study these enigmatic objects in even greater detail. Now, shifting our focus to one of the most awe-inspiring phenomena in the cosmos, let's explore the mystery of black hole jets. These powerful beams of energy, shooting out from the vicinity of black holes at nearly the speed of light, are among the most extreme and enigmatic features in the universe. But what exactly are they, and how do they help us unlock the secrets of distant black holes? Black hole jets are streams of charged particles that are ejected from the regions surrounding black holes, often extending thousands or even millions of light years into space. These jets are thought to originate from the intense magnetic fields and swirling disks of gas and dust known as accretion disks that surround black holes. As material spirals into the black hole, some of it gets funneled into these jets and blasted outward, creating some of the brightest and most energetic phenomena in the universe. One of the most fascinating aspects of these jets is their sheer power. They can emit energy across the entire electromagnetic spectrum, from radio waves to gamma rays, making them visible to telescopes tuned to different wavelengths. This multi-wavelength approach allows astronomers to study black hole jets in incredible detail, revealing insights into the physics of black holes and their environments. Distant black holes, in particular, provide a unique opportunity to study these jets. Because light takes time to travel across the universe, observing jets from black holes billions of light years away allows us to see how these structures behaved in the early universe. This helps scientists understand how black holes and their jets evolved over time, shedding light on the growth and activity of supermassive black holes throughout cosmic history. Interestingly, black hole jets are not just cosmic curiosities, they play a crucial role in shaping their surroundings. The energy and particles carried by these jets can heat up surrounding gas, preventing it from cooling and forming stars. In some cases, jets can even trigger star formation by compressing gas clouds as they blast through them. This dual role of jets as both destroyers and creators highlights their profound impact on the evolution of galaxies. But perhaps the most intriguing aspect of black hole jets is what they reveal about the black holes themselves. By studying the properties of these jets, such as their speed, structure, and energy output, scientists can infer details about the black hole's spin, mass, and the nature of its accretion disk. This makes jets an invaluable tool for probing the inner workings of black holes, especially those located at vast distances from Earth. As we continue to unravel the mysteries of black hole jets, they remind us of the incredible complexity and dynamism of the universe. These cosmic powerhouses not only illuminate the nature of black holes, but also connect us to the broader story of how galaxies and the universe itself have evolved over billions of years. Next, we'll delve into how distant black holes contribute to solving some of the universe's greatest mysteries, from dark matter to the expansion of the cosmos. Now, let's turn our attention to one of the most profound roles distant black holes play in the cosmos, their contribution to unraveling some of the universe's greatest mysteries. From the enigmatic nature of dark matter to the accelerating expansion driven by dark energy, these cosmic giants hold clues that could reshape our understanding of the universe. Distant black holes, especially supermassive ones, are deeply intertwined with the mysteries of dark matter. While dark matter itself remains invisible, its gravitational effects are undeniable. Black holes, with their immense gravitational pull, often reside in regions where dark matter is densely concentrated. By studying how black holes interact with their surroundings, scientists can infer the presence and distribution of dark matter. For instance, the way black holes influence the motion of stars and gas in their host galaxies provides indirect evidence of dark matter's influence. This interplay helps astronomers map the invisible scaffolding that holds galaxies together. But the connection doesn't end there. Distant black holes also offer insights into dark energy, the mysterious force driving the accelerated expansion of the universe. By observing how black holes and their host galaxies evolve over billions of years, researchers can track changes in the rate of cosmic expansion. Supermassive black holes, in particular, serve as cosmic markers. Their growth and activity over time provide a timeline that helps scientists measure how the universe has expanded and how dark energy has influenced this process. Another fascinating aspect is how black holes might help bridge the gap between dark matter and dark energy. Some theories suggest that the extreme environments around black holes could reveal interactions between these two mysterious components. For example, the way black holes accrete matter and emit energy might offer clues about how dark matter behaves under extreme conditions or how dark energy influences the fabric of space-time itself. Moreover, the study of distant black holes has led to groundbreaking discoveries about the large-scale structure of the universe. Their jets and radiation can illuminate vast regions of space, revealing the cosmic web, a network of dark matter and gas that connects galaxies across the universe. By observing how black holes interact with this web, scientists can better understand how dark matter and dark energy shape the universe on the largest scales. In essence, distant black holes are more than just cosmic curiosities. They are key players in solving some of the most profound questions in modern astrophysics. From shedding light on the invisible forces that govern the universe to helping us map its vast structure, these enigmatic objects continue to push the boundaries of our knowledge. As we move forward, we'll explore how distant black holes might even hold clues to the emergence of life in the universe, connecting the cosmic to the personal in ways we're only beginning to understand. Now, let's shift our gaze to one of the most intriguing possibilities: how distant black holes might play a role in the emergence of life in the universe. At first glance, black holes seem like the last place you'd expect life to thrive. After all, their immense gravitational pull and destructive power make them seem like cosmic death traps. But when we look closer, these enigmatic objects might actually hold the keys to understanding how life could arise in the vast expanse of space. One way distant black holes could influence the potential for life is through their impact on galaxy formation. Supermassive black holes, often found at the centers of galaxies, play a crucial role in shaping their host galaxies. By regulating star formation and distributing heavy elements like carbon, oxygen, and iron, black holes help create the building blocks necessary for life. These elements, forged in the hearts of stars and scattered across the cosmos by black hole activity, are essential for the formation of planets and the chemistry that supports life as we know it. But the connection goes even deeper. The intense radiation and jets emitted by black holes can create environments that, while harsh, might also trigger the formation of complex molecules. In some cases, the energy from black holes can heat surrounding gas clouds, sparking chemical reactions that lead to the creation of organic compounds. These compounds, such as amino acids, are the precursors to life. While the immediate vicinity of a black hole is inhospitable, the surrounding regions could serve as cosmic laboratories where the ingredients for life are mixed and tested. Another fascinating idea is that black holes might act as cosmic recyclers, redistributing matter and energy across the universe. When black holes consume stars and gas, they don't just destroy, they also expel material back into space through powerful jets and winds. This process can seed distant regions with the elements needed for life, potentially creating conditions where planets and eventually life could form. In this way, black holes might be the unseen architects of life-bearing worlds scattered across the cosmos. Moreover, the gravitational influence of black holes could play a role in protecting life. In some scenarios, black holes might shield regions of space from harmful cosmic radiation by bending and trapping high-energy particles. This could create pockets of relative safety where life could develop and thrive, even in otherwise hostile environments. While this idea is still speculative, it opens up exciting possibilities for how black holes might contribute to the habitability of the universe. As we continue to explore the cosmos, distant black holes remind us that even the most destructive forces can have a creative side. From shaping galaxies to seeding the building blocks of life, these cosmic giants might hold the answers to one of humanity's oldest questions: are we alone in the universe? And as we move forward, we'll delve into how studying these distant black holes could pave the way for future discoveries, bringing us closer to understanding our place in the grand tapestry of the cosmos. Now, let's turn our attention to the future, specifically how the study of distant black holes could unlock new frontiers in space exploration. These cosmic giants aren't just fascinating objects to observe. They could also serve as gateways to groundbreaking discoveries that reshape our understanding of the universe. By delving deeper into the mysteries of black holes, we might uncover technologies and insights that propel humanity further into the cosmos than ever before. One of the most exciting possibilities lies in the potential for black holes to act as natural laboratories for testing the laws of physics. The extreme conditions near black holes, where gravity bends space and time to their limits, offer a unique environment to study phenomena that are impossible to replicate on Earth. For instance, understanding how matter behaves near the event horizon could lead to breakthroughs in quantum mechanics and general relativity, potentially revealing new principles that could revolutionize space travel. Imagine harnessing the energy of black holes or using their gravitational influence to navigate vast distances across the universe. These ideas, while still speculative, highlight the untapped potential of these cosmic wonders. Moreover, the study of distant black holes could inspire the development of advanced technologies. Telescopes and instruments designed to observe black holes often push the boundaries of engineering and innovation. For example, the Event Horizon Telescope, which captured the first image of a black hole, required a global network of observatories working in perfect synchronization. This kind of collaboration and technological advancement could pave the way for even more ambitious projects, such as interstellar probes or next-generation space telescopes capable of peering deeper into the universe than ever before. Black holes also hold clues about the origins and evolution of the cosmos, which could guide future exploration missions. By studying how black holes influence galaxy formation and the distribution of matter, scientists can identify regions of space that might harbor habitable planets or other intriguing phenomena. This knowledge could help prioritize targets for future missions, whether they're robotic explorers or crewed expeditions. In a sense, black holes could act as cosmic signposts, pointing us toward the most promising destinations in the universe. Finally, the pursuit of understanding black holes fosters international collaboration and inspires the next generation of scientists and explorers. The challenges of studying these distant objects require expertise from diverse fields, from astrophysics to computer science, encouraging innovation and teamwork on a global scale. As we continue to unravel the secrets of black holes, we're not just expanding our knowledge of the universe, we're also building the tools and partnerships that will drive humanity's journey into the stars. As we look to the future, it's clear that black holes are more than just cosmic curiosities. They're keys to unlocking the next chapter of space exploration. And as we prepare to delve into the final facts about these enigmatic objects, we'll reflect on how they've shaped our understanding of the universe and our place within it. Now, let's shift our focus to one of the most intriguing mysteries in astrophysics: the eventual fate of black holes. While black holes are often thought of as eternal cosmic vacuums, even these titans of the universe aren't immune to the passage of time. The theoretical end of a black hole is a concept that challenges our understanding of physics and offers a glimpse into the far, far future of the cosmos. At the heart of this mystery is a phenomenon known as Hawking radiation, named after the renowned physicist Stephen Hawking. According to his groundbreaking theory, black holes aren't completely black. Over unimaginably long timescales, they emit tiny amounts of radiation due to quantum effects near their event horizons. This process causes black holes to lose mass very slowly, and as they do, they begin to shrink. For a supermassive black hole, this process could take trillions upon trillions of years, far longer than the current age of the universe. But eventually, even the most massive black holes could evaporate entirely, leaving behind nothing but a faint burst of energy. For distant black holes, this process is even more fascinating. Because they exist billions of light years away, we're essentially observing them as they were in the distant past. This means that by the time their light reaches us, some of these black holes might already be in the late stages of their life cycle, slowly fading away through Hawking radiation. Studying these distant black holes could provide clues about how this process unfolds and what it means for the ultimate fate of the universe. But here's where things get even more mind-bending. As a black hole evaporates, it doesn't just disappear quietly. In its final moments, it's theorized to release a tremendous burst of energy, equivalent to the explosion of millions of atomic bombs. This final burst, often referred to as a black hole explosion, would be one of the most dramatic events in the cosmos. Yet, because it happens over such an incredibly long timescale, it's something we're unlikely to ever witness directly. Instead, we rely on theoretical models and observations of distant black holes to piece together this cosmic puzzle. The death of a black hole also raises profound questions about the nature of space, time, and information. According to quantum mechanics, information about matter that falls into a black hole should never be lost. But if a black hole evaporates completely, what happens to that information? This is known as the black hole information paradox, and it remains one of the greatest unsolved mysteries in physics. Distant black holes, with their long lifespans and unique properties, could hold the key to unraveling this enigma. As we ponder the eventual demise of black holes, we're reminded of the impermanence of even the most powerful forces in the universe. These cosmic giants, which once seemed invincible, are destined to fade away, leaving behind only echoes of their existence. And as we continue to study distant black holes, we're not just exploring their life and death, we're uncovering the fundamental laws that govern the cosmos itself. With this in mind, let's turn to our final fact, where we'll reflect on how the study of black holes has transformed our understanding of the universe and our place within it. As we reach the final chapter of our journey through the mysteries of distant black holes, it's worth taking a moment to reflect on how these cosmic enigmas have reshaped our understanding of the universe and our place within it. The study of black holes, especially those billions of light years away, has been nothing short of revolutionary. These colossal objects, once thought to be mere curiosities, have become windows into the deepest secrets of space, time, and existence itself. Through the lens of distant black holes, we've gained unprecedented insights into the origins and evolution of the cosmos. They've shown us how galaxies form, how matter behaves under extreme conditions, and even how the universe itself might have begun. Each discovery, from the detection of gravitational waves to the imaging of black hole shadows, has pushed the boundaries of human knowledge and challenged our most fundamental assumptions about reality. But perhaps the most profound impact of studying black holes lies in how they've reshaped our perspective on humanity's place in the universe. These distant giants remind us of the vastness of space and the fleeting nature of time. They force us to confront questions about the ultimate fate of the cosmos and the limits of our understanding. In doing so, they inspire both humility and curiosity, a recognition of how much we still have to learn and a drive to keep exploring. Black holes also serve as a testament to the power of human ingenuity. From the theoretical breakthroughs of Einstein and Hawking to the technological marvels of modern telescopes and detectors, our ability to study these distant objects is a triumph of science and collaboration. It's a reminder that, even in the face of the universe's most daunting mysteries, we have the tools and the determination to seek answers. As we conclude this exploration of the universe's most distant black holes, let's not forget the bigger picture. These cosmic wonders aren't just objects of scientific study, they're symbols of the endless quest for knowledge. They remind us that the universe is full of mysteries waiting to be uncovered, and that every discovery brings us closer to understanding our place in the grand tapestry of existence. Thank you for joining us on this incredible journey through the cosmos. If you've enjoyed this deep dive into the mysteries of black holes, don't forget to like, share, and subscribe for more space-related content. Until next time, keep looking up and keep wondering about the infinite possibilities that lie beyond the stars. As we bring this cosmic journey to a close, let's take a moment to reflect on the 50 incredible facts we've uncovered about the universe's most distant black holes. From their mind-bending gravitational pull to their role in shaping galaxies, these cosmic giants have revealed secrets about the origins of the universe, the nature of time, and even the possibility of alternate realities. Each fact has been a stepping stone in our quest to understand the cosmos, reminding us just how vast, mysterious, and awe-inspiring the universe truly is. Distant black holes are more than just scientific curiosities. They're keys to unlocking some of the greatest mysteries of existence. They've shown us how galaxies form, how matter behaves under extreme conditions, and how the universe itself might have begun. They've challenged our understanding of physics, pushed the boundaries of technology, and inspired us to keep exploring the unknown. Whether it's the discovery of the oldest black hole, the detection of gravitational waves, or the mind-blowing concept of Hawking radiation, each revelation has brought us closer to understanding the grand tapestry of the cosmos. But the story of black holes is far from over. Every discovery raises new questions, and every answer leads us deeper into the mysteries of space and time. These distant black holes remind us that the universe is a place of endless wonder, full of secrets waiting to be uncovered. They inspire us to keep looking up, to keep asking questions, and to keep pushing the limits of what we know. Thank you for joining us on this incredible journey through the universe's most distant black holes. If you've enjoyed this exploration, don't forget to share your thoughts in the comments below. What fact surprised you the most? And if you're as fascinated by the cosmos as we are, make sure to hit that like button, subscribe to the channel, and turn on notifications so you never miss out on more space-related content. Until next time, keep your eyes on the stars and your mind open to the infinite possibilities of the universe. The cosmos is waiting. Let's keep exploring together.